tiny bit, right? Because when we start from here, the cost so far is not 10, it's actually 0 because we're pretending like we actually started from here, right? And that will be easy to handle for us if we recursively implement this solution. So what I'm saying is, for us, if we started at 1, we'd put a path over here on the right and then get to 3, and the cost for that would be 15, not 25 as we have down here. And the other path where we go left, we go jump to position 2 and then jump to position 3, that would cost us 15 plus 20, which means the total would be 35 rather than 45, right? So not 45 over here, it would actually be 35. The main point of what I'm trying to show you is there's repeated work here, right? If we take this solution as it is, it's exponential because it's a decision tree. Each node is going to have 2 branches, right? Up to 2 branches, and we're going to keep doing that until we get to the base case, right? Which is index 3. So what's the possible height, the max height of this tree? Well, we can have a potential level for every single position in the input array, right? So the height of the tree is going to be n, which is equal to the length of the cost array, right? So n is equal to the length of the cost array, and we know that we can have 2 branches for every single node, so the time complexity comes to 2 to the power of n. But as we just showed, there's a lot of repeated work that we're doing. If we eliminate that repeated work, we can actually get this time complexity down to big O of n. Because what we're noticing is, to solve the original problem, which is what's the minimum cost if we start at index 0 to reach index 3. To solve this problem, we're asking a couple more questions. We're basically solving the subproblem. We're asking, okay, how about to solve this problem, we have to first figure out if we're starting at index 1, what's the minimum cost of reaching index 3? And to solve this problem, we're asking another subproblem down here. Okay, what about if we start at index 2, then what's the minimum cost to arrive at index 3? So if we cache this repeated work with a hash map or something so that we don't repeat the same problem multiple times, what I'm saying is, over here, you can see that we start at index 2 and we want to know what's the cost to reach index 3. Well, it turns out that it was 20, right? From 2 to get to 3, it costs 20. So then when we are trying to solve that same subproblem over here, starting at index 2, how much does it cost to get to index 3? Well, it was 20. We don't actually have to run through that because we already solved that problem over here, right? So that's the main idea of how we can get this to big O of n. The reason it's big O of n is because we have n subproblems. We're asking, okay, from index 0, how long does it take to get to 3? From index 1, how long does it take to get to 3? From index 2, how long does it take to get to 3? So that will be an O of 1 operation for each position in the array, which will be n time complexity. It'll also be O of n memory complexity. And if we take this idea of caching the recursive solution, we can actually get an iterative solution that I'm going to show you now, which will have the same time complexity and pretty much the same memory complexity as well. So now let's actually go over the real dynamic programming solution, which will actually have a slightly better memory complexity because we can actually use the input array itself that we're given, and we could actually even just use 2 single variables to do the DD solution. Let me show you why. So we noticed that to solve the original problem, right, starting from index 0, what's the minimum cost to reach the out of bounds position or the top of the staircase, we first have to solve the subproblem of starting from 1 and starting from 2, right? So basically this has a dependency of this and this, but we also learned that this has a dependency of this, and basically every one of these cells has that dependency. So how about we actually solve this problem from right to left rather than from left to right? Let's solve the subproblems first and then solve the original problem. Okay, so does that mean we're going to start from index 2? We want to know what's the cost for this to reach index 3? Well, it has 2 choices. It can do 1 jump or 2 jumps. The second jump doesn't do anything because it also goes out of bounds, right? The first jump will go out of bounds, so that's enough for us. And what's the cost to reach 3? Well, it's going to be just 20. Yes, that works, so we can just leave 20 here, right? So from index 2 to reach out of bounds, it takes 20. But what about from index 1? Now we kind of get into one of the more interesting cases, right? From here, we can also do a single jump. So then we're asking, okay, if we do a single jump, it'll obviously cost us 15 to do that single jump, but also the value that should be in this position is from index 2, how long does it take to reach index 3? Because then what we can say is, okay, for index 1 to reach index 3, we can just take 15, which was this jump, and then 20, which was the remainder, right? The remainder to reach index 3. So we can, in this position, we can put 15 plus 20. But hold on, because there's actually 2 paths, right? We already handled the single jump case, but what if we do a double jump from index 1? Then what's the cost that we put here? Well, we put 15 because that's the cost of making the double jump, but then we'd want to also add the value that goes here to that total result, right? Because from index 3, how long does it take to reach index 3? It's kind of a weird question logically to actually ask, but just to make the math work out, the easiest number we can put here is 0, right? Because if we're already at index 3, it obviously doesn't cost anything to stay here. So that's the reason why we're putting a default value here of 0. Now we actually have to look at 2 choices, right? Because one possibility was we go here, make a single jump to 2, and then go to 3, right? The cost of that will be 15 plus 20. Another possibility is we start here and then just do a double jump to this position, right? And the cost for that is going to be 15 plus 0 because there's a 0 here. So we want to take the minimum of both of these values. What's smaller, 35 or 15? Of course, 15 is smaller, so we're going to put the minimum of these 2 computations in this position. And the good thing is it's already 15. And last, we're going to start from index 0. We're going to see, okay, 10 plus the cost, 10 is the cost for making 1 jump. And then from here, from index 1, what would be the cost to do the remainder of reaching index 3? It's just going to be the value that's here, which is already 15. So 10 plus 15 is 25. That's one possibility. The second possibility would be making a double jump. So from here, a double jump, 10 plus 20, which is the value here, is 30, right? So we want to take the minimum of those 2 values. Of course, 25 is smaller than 30, so we put 25 in this position. So now in this array, every single index represents the entire cost it would take from this index to reach the end of the array, or the top of the staircase. From 2, it would be 20. From index 1, it would be 15. And from index 0, it would be 25. Now, what value do we actually want to return? Remember, we can only start at index 0 or index 1. We can't start at index 2, and we definitely can't start at the top of the staircase. So what we're going to return is just going to be what's the minimum of the first 2 values in this array. Of course, the minimum of these 2 is 15, so we can just return 15. As you can see, the time complexity was definitely big O of n. We just iterated through the array in reverse, and the memory complexity is technically big O of 1 because we're just using the input array itself, and you actually don't even need to use the input array. You don't need to write over the input array because if you notice, as we go in reverse, this value only depends on the next 2 values, and this only depends on the next 2 values. So really, if you wanted to, you could just keep 2 variables in memory rather than even writing over the entire array. And then as you go in reverse order, you could update those variables to the correct values. But it's your choice of how you want to code it up. Speaking of code, now we can finally jump into the coding solution. Okay, so now let's jump into the code, and this is the same example that we were basically working on. And remember, what we wanted was to just have another extra 0 at the end of the array, just to make the math work out easily for us. So that's what we're going to do to this input array. We're just going to append a 0 value to it, and then we want to iterate through this array in reverse order, right? So what index are we going to start at? Well, in the drawing, I started at this index, but remember, what we're going to be doing is taking this and then looking at the next 2 values that come after it. Of course, for the last index, or this index that I'm showing, there aren't 2 values that come after it. So we should actually start at this index, and that makes sense for us because we're not actually going to be updating this value because we're just going to take 20, add it with 0, which doesn't change this value at all, right? So that's why we're going to be starting at this index. How we can get this index is basically the entire length of the array. We know that the entire length of the array minus 1 will give us the last position, right? Length minus 1 will give us this position. So really, we can do length minus 3, which will give us this position, which is where we want to actually start at. So we're going to do the length of the cost array minus 3. 3. And this is just how you do it in Python, at least with a for loop. And we're going to decrement. We're going to keep going all the way until we reach the beginning of the array, and we're going to decrement by 1 each time. If you're not familiar with Python, all we're doing is just iterating, starting at this position in reverse order from this array. So remember what we want to do for cost at index I. What we want to assign this to is really the minimum of cost of index I plus cost of index I plus 1, right? Because from here, if we make a single jump, we're going to land here. So we want to add the value at that position that we land at to the original position. The second choice is if we make a double jump. So I'm just going to copy and paste this because it's pretty similar. If we make a double jump, this is what the computation will be like: cost of I plus cost of I plus 2. But if you want to actually simplify this line of code, you can see that since both of these computations have cost of I as the first value, we can actually just remove cost of I from both of these and actually just take the minimum of these two and add it to the original value. So we can just change this line to this, right? Take the minimum of these two and add it to cost of I. Yeah, that's the entire code. Just iterate through it in reverse order, do the computation, and then the only thing you have to return is the minimum of the first two values of cost of I, so cost of 0 and cost of index 1. And the main reason that this works is because we're guaranteed that the cost array is going to have at least two values. If we weren't guaranteed that, then we couldn't necessarily do this line over here. But let's run it to make sure that it works. Let me just delete this first line up above so we don't get any errors. And as you can see on the left, yes, the solution works and it's pretty efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider checking out my Patreon where you can further support the channel if you would like. And hopefully I'll see you pretty soon. Thanks for watching.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem unique paths 2. We have solved the first variation of this problem. This one is pretty similar. We're given an m by n grid, so this is our grid down here. We are going to start at the top left position where this robot is. I don't really pay too much attention to the entire story. We can either move down or to the right, and anytime we get to a different position, it's the same. We can either go down or to the right. But we can only move along positions that are marked with a 0. So any of these free positions are going to be marked with zeros. But this here is an obstacle, and that's going to be marked with the value 1. And that means we are not allowed to place our robot here. We can't go through this position, so it's like blocked off. Now our goal is to get to the bottom right position. That's our target position. And what we're looking to do is just count the total number of ways that we can reach that position. So just taking a look at this grid, how many ways are there? Well, we can go to the right and then down, that's one path, and we can go this way. So there's really only 2 paths in this grid. But if we had a larger grid, we could have more unique paths that lead to the target, well, depending on how many obstacles we have as well. If there wasn't an obstacle in this position, we would have a lot more. We would be able to reach the target position this way, or reach the target position this way, or this way, or this way, or even this way, and this way as well. So the easiest way to solve this problem is brute force, and using this logic, we can come up with the more optimal solution, which is going to involve dynamic programming, but it's not too crazy. Taking a look at the brute force solution, it's best to handle this recursively, so we would do it with with a depth first search. The main thing we'd want to pass in is our row and column, because we're here. We have two choices no matter where we are. We can either go down, which is to take our row and increment it by 1, or to move to the right, which is to take our column and increment it by 1. And then recursively, what we want to ask ourselves is to count the number of unique paths starting from here. What we can do is just count the number of unique paths from here and the number of unique paths from here, and then take those and then add them up, and then we will have the total number of unique paths from here. But then the catch is, how do we compute the ones from here? Well, recursively, we'd pretty much do the same thing. Go down, count the paths from here, or go to the right and count the paths from here. And basically, that's how our recursion would work. We could imagine like a decision tree, but the base case is going to be when we either, suppose from here we go out of bounds too far down, or maybe from here we go too far to the right. That's a base case, and that would return 0. There's 0 paths if we go out of bounds. The other base case is if we actually reach the target position, then we'd say 1. So from here, how many ways can we reach the target position? 1. What about from here? How many ways can we reach the target position? 1. So a good way to like initialize this would be to like place a 1 here, or at least imagine that there is a 1 here, and then our math kind of works out for all the rest of the positions. And the good thing about this is that while recursively this would be an exponential solution, but when we implement caching to this, caching as in anytime we compute the value that goes in any of these positions, we never want to recompute it, because for maybe this, it's pretty simple. We just look down and then we can get the value here. But for somewhere like this, there might be multiple paths and we don't have to retraverse those paths recursively, so we do caching to eliminate repeated work. So we'll have like a 2-dimensional DP grid that's the same size as this. I usually use a hash map, but it's up to you. This will though lower our time complexity. Instead of being exponential, will just be the size of the grid, which is n times m. That's also the amount of memory we're going to need for this DP solution. So let me quickly show you the recursive solution, but there's actually a way to optimize the memory to get this to actually be big O of n, or you could get it down to big O of m, but basically like one of these rows is the memory that we need, and that's like the true dynamic programming solution. So I'll show you that afterwards. So this is the recursive solution. I'll go through it pretty quickly. The first thing I like to do is just get the dimensions of the grid. So m is the number of rows, n is the number of columns, and then I'm using a hash map to use as our cache. So what I did is exactly what I said in the drawing explanation. I'm basically initializing the bottom right position to be 1, because we know that's kind of our base case, but this wouldn't necessarily be required, and you could have instead used like a 2-dimensional grid that's n by n, but I just like to use a hash map for recursive problems. We're passing in the row and column into our recursive function because this function is defined in the outer function. We already have a reference to our DP cache and to these variables as well, so I'm not passing them in. And there's a few base cases here. One is if we go out of bounds. So if our row becomes equal to m or our column becomes equal to n, then we want to return 0 immediately. The third case is that the grid position is blocked. We know if this value is a 1, then it's blocked. We can't traverse through there, so we would return 0 in that case. That's the number of unique paths. The other case is that we've already computed the value at this position. So this is already in our cache. This key is in our DP hash map, so we would return the value that was already stored there. Now, if that's not the case, that's where we actually do our recursion here. So counting the paths at row plus 1, counting the paths at column plus 1, adding them together, storing them in the hash map, and then returning that value. And then finally, to get our result, we just call DFS starting at the top left. So now to actually understand the true dynamic programming solution, which can be really helpful for more difficult problems, I would say this is one of the more easy 2-dimensional dynamic programming problems. So it's a good example to practice on. So let's talk about the real dynamic programming solution, and let's consider this same example over here. Even though it's a pretty simplified one, it will still get us all the information we need. Even our caching solution is basically computing all the values that go inside of this grid to eventually get us the value at the top left of the grid. So the idea behind dynamic programming is that we can compute these values bottom up. Instead of doing them recursively, instead of trying to compute this one first and then that leads to the subproblems, we can immediately start with the subproblems and then compute them in such an order that we can eventually arrive at the ultimate solution. So that's exactly what we do. We start at the bottom right and then fill these values in reverse order to get us the top left value. But some people do it the opposite way. Some people don't like to traverse arrays in reverse order and then the rows in reverse order as well. The interesting thing about this problem is that it's symmetrical in that if you count the number of paths starting from here to the bottom right, that's the exact same as counting the paths from the bottom right up to the top left. So you can do it the same way that you want to. You can do from top right to left, or you can do it like bottom up like I'm doing. It's up to you. I prefer to do it bottom up because that kind of preserves like the context of the problem, because in the context of the problem, we're allowed to go down and to the right. So if we kind of do it the opposite way, we'd have to consider us going either to the left or above, but that's a pretty small point. Now to actually start filling in the values, we know that the bottom right is always going to be a value 1, so we can just initialize it like that. And let's just mark this spot just to indicate that we have an obstacle here, but we still need to fill the value in. Going in reverse order, so what value would we put here? Well, we want to add the value to the bottom and the value to the right. And when we go out of bounds here, we can just assume that the value is 0 as like the default value, so then the value we put here is 1. What about over here? Same thing, go to the bottom and to the right, so we put a 1 here. What about over here? Same thing, we go bottom, that's a 1. When we go out of bounds to the right, we also assume there's a 0 here, so we just put a 1 over here. And then here, when we get to the obstacle, we just want to skip it, so we just either leave a 0 here or put a 0 if there's not already one. And we just keep going like that. So from here, we'd get a 1, and here we'd have a 1, and then finally at the top left position, we'd look down, look to the right, add those together, we'd get a 2. That's the result that we're looking for. So it's really that simple, but the way we coded this up, we have the entire grid in memory, but it's actually not required. We don't need to have this n by m grid in memory, because if you notice something, every time we look for a value, suppose this one, what we would do is look to the bottom and look to the right. Anytime we're computing a position, we only need the previous row in memory. By the time we get up here and we're trying to fill these values in, we don't really need this row in memory anymore. We just need the previous row. Then you think, well, we only need at most 2 rows in memory, but actually we need even less than that. We only need 1 row in memory. Let me show you what I would do. We have these values here. I'm going to show you how to fill these values in if we were doing it in place. So how would we get the value here? Well, we'd look bottom, the value that's already stored here, and look to the right. So it's 1 plus 0. So then we'd put a 1 here. But what I'm going to do is actually place it over here, because my argument is that once we compute the value here, we actually don't need this value to even be in memory. So let's just assume that this value actually is taking up this spot, but I'm just illustrating to you that this doesn't matter anymore. We're never going to use it again. We only need these 3 values, basically the size of the row. And now to get the value here, well, it's an obstacle, so it doesn't matter anyway. So we put a 0 here. Once we put that 0 here, we would never need this value anyway. And then finally, when we get to this position, we want to look to the bottom because we want to know how many paths we can get going down, and we want to look to the right because we want to know how many paths we can get going from the right. But in reality, these values are still going to be stored in this position. We're not going to allocate extra memory for them. So 1 plus 0 is going to give us a 1 here. So as you can see, it's possible to fill a row in place without allocating extra memory. So we just need a single row in memory, and that's the idea I'm going to use to solve this problem. And I'm going to do it in reverse order, but you don't necessarily have to. So what I'm going to do is just initialize the dimensions again. This time I'm going to have a DP row, which is going to be filled with zeros. It's going to be the size of any of these rows. And the last value is going to be set to 1, kind of like I did in the drawing. And that will get us to the most optimal solution. So what I'm going to do is then go through the list of rows in reverse order. So we have m rows, and I'm going to go through them in reversed order. So r is going to be the index of the row. And I'm going to go through every column in reversed order. So we can do that just like this. And there's going to be a couple cases. We know the really simple case is if the value in the grid is a 1, then we know it is blocked off. So we can't go anywhere. we can't do anything. So what we are going to do at that point is just say dp at this position, at this column, is going to be equal to 0. And then we have a couple cases. And then otherwise, what we would do is say dp at this column is going to be equal to the value below it. What's the value below it? It's just going to be at dp of column. Because we're doing this in place, remember? To get the value in the previous row, what we would do is just get the same value in this dp row at the same index. So this is the bottom.
You're back. Let's get it locked in. Lock in. Doink it, doink 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 doink.
Bottom value, and to get the value to the right, we say add dp at column plus 1. So that's how we would get the value. Remember the couple edge cases where we go out of bounds? If we go out of bounds going to the bottom, well, in this case, that's never going to happen because we are initializing our dp array with a bunch of zeros. This would never go out of bounds if we're going to the bottom, but going to the right, we might go out of bounds. If c plus 1 is equal to n, for the last value in our row, we're going to go out of bounds. So what we can do here is first add an else if, because if this doesn't execute, that's when we would want to do this, but also say if c plus 1 is equal to n, that means we went out of bounds, or we could say c is equal to n minus 1. Either way, that means we went out of bounds. So what we're going to say is c plus 1 is less than n. If that's the case, then we're allowed to do this. But if this is not true either, then what we would say is the value to the right is out of bounds, so we're not going to add it. So the only thing we're going to do is add the value below to this. Well, not to this, but we'd say the value to the bottom plus 0 is what we're going to put here. But notice how that dp of c is equal to dp, the bottom value, plus the value to the right, which is 0. This is not doing anything. This is just like an assignment. It's not doing anything, so we don't need it. But I wanted to explain why we don't need this. But I think it's kind of obvious just looking at it. So we don't actually need this else case. It's not doing anything. And then we just have this code, which is pretty much all we need. By the time this is done, the value at the top left position, dp of 0, will have the result, so we can go ahead and return it. Now let's run the code to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.
So we take n, which equals the length of grid, and then we get length of grid of index 0. Okay, so starting point. dp equals 0 times n plus 1. dp n minus equals 1. For r in range, so the row in range m minus 1, we're going to be working backwards. -1, -1, enter each one. For c in range, for column in range n minus 1, -1, -1. If grid rc dpc is equal to 0, else dpc plus equals dpc plus 1. Okay? Return dp0. Okay? Obstacle grid. Row call, column, nice. Maximum subarray. Given an array of integers nums, find the subarray with the largest sum and return the sum. A subarray is a continuous, non-empty sequence of elements within an array. Example: 2, -3, 4, 2, 1, 4. Subarray. We could just... So maybe a greedy approach, which is very brute forcing and go down the entire list. Makes the number smaller, remove it. Okay.
Let's solve Leetcode 53 maximum subarray. So we're given an integer array of nums, and we want to find the contiguous subarray containing at least one number which has the largest sum, and then we want to return only the sum. So this array has positive numbers and it has negative numbers. So that's what we have to keep in mind. In this case, the largest sum is 6, and it's just this middle portion of the array. So the first thing you might try is just compute every single subarray, right? So let's first compute every single subarray starting at -2. There's one subarray, there's two subarrays, there's three subarrays, and we keep doing that until we got to the end, right? And then we can repeat the process for the second number. So the subarray starting at 1 here, another subarray starting at 1 here, another subarray starting at 1 here, all the way until the end. Now we could repeat that same process for every number in the array. So let's just write the pseudocode to see what kind of complexity this would yield. So let's say we're starting, the I is going to represent the starting value. It's going to range from 0 all the way to the last number, n-1, or the last index, n-1. And then we want to get the ending index. So I'm going to use j for the end of this subarray. So we're going to start at I, and we're going to keep going until the end of the subarray, or until the end of the entire array, n-1. So this represents the start, I represents the start, j represents the end. Now we actually want to compute the sum of the subarray, so we're going to have a third loop for that, right? Let's use k. K is going to range all the way from I to j, right? Because that's what represents the subarray. And then in here we compute the sum, right? Now, obviously, this is really inefficient, right? The time complexity is n cubed. It's obvious because we have three for loops. So let's try to expand upon this. Let's see if we can make any shortcuts to improve it. So the most obvious thing you'll probably notice is that we can save time when we're computing a subarray. So if let's say we computed this subarray, right, and then we want to compute the next subarray with just one added element. Well, we can save the result of this, right, and say it's our current sum or whatever. And then to compute this subarray, we just have to add this number over here, right? So we can just say current sum plus -1. And so this can save us time. Let's take a look at the time complexity of this solution. So we're going to have another for loop, which is going to represent the start. So start is going to range from 0 all the way to n-1. And we're going to have another loop for the end of the subarray. J is going to range from I to the last index, n-1. And then inside the loop, we're going to maintain our current sum and simply just add the number j each iteration of the loop, right? So this is a little more efficient, O of n squared. It's a pretty easy optimization to make, and it improves your solution a lot. But can we do even better than this? So now the question you should ask yourself is, do we have to compute every subarray starting at every single value in the array, right? Do we have to start at every single value and compute every subarray that comes after it? I don't think we do. Remember, we're trying to find the maximum subarray. We can use that knowledge to help us make a shortcut. So let's take a look at this. We have a -2, right? So when we're starting here, that's going to be our max sum so far. Then we get to -2 plus 1. So this is -1 so far, right? Do we actually need this negative number? The negative numbers don't contribute anything in this case, right? So we can basically ignore that value, right? Once we get here, we can basically say this negative value, this negative prefix that came before +1 isn't going to help us at all. So let's not even consider it. So next we get to this -3. Now up until here, our total sum is -2, right? So then we get to this 4. This is a negative prefix that came before it, -2, right? So we can say up until this point, we're not even going to consider what came before. So this 1 and -3 aren't going to help us at all. Just ignore them. Now we get to a -1. So the prefix that came before this was a +4. So we're going to not delete it from our list. We're going to keep that +4 and add it to this -1. So now we're going to be at 3 so far. Now we get to a +2, right? Even though there's a -1 that came before it, well, there was a +4 that came before that. So if we get rid of this -1, we also have to get rid of the +4, which we don't want to do. Remember, we have to keep the subarray contiguous. So I'm not going to chop this portion off. I'm going to keep it. Now we're going to add 2 to it, so now we're going to be at 5. Then we're going to get this 1. We're going to add it and get our subarray of 6. And this is the result so far, but let's keep going and see what happens. Next, we'll have a -5, right? So -5, now we're at 1. So obviously, we decreased our subarray, but we know this -5 is not going to be deleted because we had a +6 portion comprised of these 4 elements that came before that. Lastly, we get a +4 again, add that. Our sum is still 5, so we see that the max subarray was this portion of these 4 elements, which totaled to 6. Now, this was a linear time algorithm. It's kind of like a sliding window, right? We keep incrementing our right pointer as we go through the array, right? But our left pointer keeps getting shifted if we ever have a negative prefix like this -2 or this -2 portion comprised of these 2 elements. So anytime we get a negative prefix, we remove it. And for me, it kind of helps me to think about this as like a sliding window. And since it's a linear time algorithm, the overall time complexity is big O of n. We didn't need any extra memory. We just had to go through the array, removing any negative prefix as we computed the total sum. Okay, so now let's code it up. So we can initialize our max subarray to the first value in the array. That's like the default value that we're going to give it because we have to give it something, and it can't be 0 because we know we have negative values in this array. And we know the array is non-empty, so the 0th value of the array is always going to exist. And we're going to be constantly computing our current sum, so I'm going to initialize that to 0. So let's go through each number in nums. Now remember, if we had a negative prefix, we're going to remove that portion from our current sum. So the way that we can check this is just check if current sum is at any point negative. If it's less than 0, we're just going to reset it back to 0. And then after that, we can add our current number to this. This will make sure that we're always computing the maximum that we can. Now, this current sum could be the possible maximum, so we're just going to update our max subarray to the maximum of itself, as well as the max that we just computed. After we're done with that, we'll return whatever we computed as the max subarray.
I hope this helped show you kind of the intuition behind the solution of this problem. If it was helpful, leave a like and subscribe, and thank you for watching.
Okay. So he did not take the brute force approach. He did not take the recursion approach. He did not take the bottom-up approach. He took...
Some could be the possible maximum, so we're just going to update our...
So we take max sum from the current subarray. Current sum, which is equal to nums, the first index value. So for nums, single num, in nums, if current sum is less than 0, we can just make the current sum back to 0. And we can do current sum plus equals num. Then we want to find the max between these two. So we just take the max of max sub and then the current sum. And after that we can return max sub. And this should now give us the most greedy search approach. Single num's my fault. Huh. So if current sum needs to equal 0. That's where I messed up. Sorry, guys. There we go. Nice, nice. Intervals. Given a medium interval where intervals I equals start I, end I, merge all overlapping intervals and return a given array. Huh. Okay.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve merge intervals. We are given an array of intervals with a start and an end value. So an interval is a start and an end value. You can think of it like a class or a meeting or some kind of time period or whatever. And for each of these intervals, we want to take all the overlapping intervals and then merge them. And then we're going to have a new output array of intervals. And since we merged the overlapping intervals, the result is going to be non-overlapping. So in this case, we see we have interval 1, 3 and 2, 6. So these two are overlapping. We can merge them into one interval 1, 6. The remaining two intervals are non-overlapping, so they do not get merged. And then we see that the output has 3 on intervals, one that we had to merge to get, and then the 2 original. And the second example just basically clarifies that if we have one interval 1, 4 and a second interval 4, 5, now these aren't technically overlapping in a sense, right? Like we have 1 to 4 and 4 to 5. So they clarify that these two actually do count as overlapping. So what's a good and efficient way to solve this problem? Let's say we're given the exact same 4 intervals that we were given in the original example, but notice this time they're out of order. This one is 1, 3, this one is 8, 10, this is 2, 6. It was originally over here, right? They had given the input to us in sorted order, right? So that's kind of a hint that it might be helpful for us to keep our intervals in sorted order. But what's a good way to kind of visualize what's actually going on with these intervals? These numbers are pretty descriptive, but it's better to have a picture to look at. So I'm going to draw a number line, and we're going to start at 0 because they clarify for us in the problem that any interval is not going to start at like a negative value, so we can start at 0. So let's just start putting these intervals into our number line and see what happens. So we have 1, 3, so I'm going to have a line going from 1 to 3, which is over here. So this interval is length 2. We'll have an interval going from 8 to 10, another interval of length 2. We'll have an interval from 15 to 18, and the last interval is from 2 to 6. So notice this time we actually do have an overlapping interval, 2 to 6. So I'm going to draw it above. So I'm going to draw it where it's obvious that we have 2 intervals that are overlapping. Now, when you actually draw out the number line, it kind of becomes obvious that it would be very helpful
helpful for us to take these intervals and sort them based on the start value. We don't care so much about the end value because we want to go through our number line starting at the beginning, starting at the start value, going to the next start value, going to the next start value, and then continuing that, because this allows us to detect. So for example, we look at this interval first. We know it goes from 1 to 3. Next, we look at the second interval. It goes from 2 to 6. And since we just looked at the previous interval over here, we know that this one overlaps with this one. So what are we going to do? We're going to merge them together into a new interval. So it results in a new interval from 1 to 6, because remember, ultimately we are trying to merge the intervals. And then we go to our next starting position, which is 8. So we have an interval from 8 to 10, and we know it does not merge with this one because they're non-overlapping. We got some space over here, right? Lastly, we go to this interval, and it goes from 15 to 18. We know it does not overlap with this one. There's all this space in between, right? So just to reiterate, we're going to take our input list of intervals, sort by the start value of each interval, and then we're going to iterate through each start value, right? Starting at the first one, then the next one, then this one, then this one, and where each time we're going to check, okay, does the current interval, does the most recent interval overlap with the previous interval? If it doesn't, we don't do anything. If it does, which it did in this case, then we can merge them into one interval. Now, it might seem unnecessary to even have a picture like this because this interval problem is actually straightforward, right? We just sort and then we merge the intervals. But there are a lot more difficult interval problems where I'm telling you, drawing a picture like this, drawing a number line to understand what's actually going on makes the problem a lot easier to solve. So now let's write the code. Remember, we are sorting the entire input, and then iterating through the input, so the time complexity is going to be big O n log n, where n is the number of intervals that we're given. So thankfully for us in Python, it's pretty straightforward to sort. We can just take interval, sort, and what's the key we're sorting by? Because remember, we're sorting a list of pairs, so the key is going to be in Python, a lambda function. So in this case, I is going to stand for the interval, and what value of this interval are we going to use? We're going to use the first value, so at index 0, we're sorting by the start value. If we want to sort by the end value, this would be I of 1, but we're going to sort by the start value only. And so let's also declare an output where we're going to put the merged intervals. So I'm not going to initialize this to empty. I'm actually going to take the first interval and have it inserted into the output just so I can avoid an edge case. So we have initialized the interval. So now we're going to iterate through every single interval in sorted order. And technically, we can skip the first one because we already added the first interval into the output. And instead of just having the interval itself, we know we're going to use the start and end value, so I'm just going to extract them like this. And so how do we know if the interval is overlapping with the most recent interval? Well, we can get from our output, this is why I added one, so we can avoid the edge case. From our output, we can get the most recently added interval and get the end value of it, because that's what we need to know if it overlaps. So the end value of the most recent interval, we'll call it last end. And we're going to check out the current interval we're at, the start and end value we're iterating through. If the start is less than or equal to the last ending value, that means they're overlapping. The equal is important because they told us in the second example that we are counting equal as overlapping. So if they are overlapping, what are we going to do? We're going to merge them. How do we merge them? Well, all we have to do is take the most recently added interval and take the ending value of it and set it to the max of itself, which we already have in last end, and the max of the current end value that we're at. And the reason we need to take the max is, what if we had two intervals starting at 1, 5, and the second interval is 2, 4? Because we would iterate through them in this order because this has a starting value of 1, this has a starting value of 2, but notice how this actually has a larger end value than this one. So if we just take 4 and merge this together and set this to 4, we're actually making the interval smaller. We want to keep the 5 because merging these two together is going to actually result in 1, 5. So in the case that they're non-overlapping, what are we going to do? Well, we don't have to merge, but we do have to take that interval and still add it to our output. So we're going to take start end and just add it to our output. So what would be an example of that? Well, what if we had 7, 8, right? These two intervals are non-overlapping, so the result would actually be itself, right? We don't have to make any changes. We don't have to merge. We can just leave it as it is. And that's actually it. So we didn't really have to do anything. Since we used the built-in sort, we took care of the main part of this problem, and all we have to do now is return the output. And so this is a pretty efficient solution. I hope this kind of explained a little bit of the intuition, and you kind of have like a visual picture of what is actually going on as we run this algorithm and why we're doing it the way we are. And I hope this was helpful. If you enjoyed, please leave a like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. And I hope this was helpful.
Okay. Intervals, sort, we do a key, we can do a lambda pair. There we go. Output is equal to intervals 0 for start and in intervals. Last end is equal to output 1 if start and output -1, 1 max last end else output append start end turn output. We could take a brute force approach. Cool. Not bad. Huh. Why am I not understanding this?
Hey everyone.
It's like a little break. Got using the bathroom.
Welcome back, and let's write some more neat code today. So today let's solve the problem greatest common divisor of strings. We're given two strings s and t, and we say that t divides s if and only if one of the strings can be made up by adding the other string multiple times. We can add it twice or 3 times or more times. Maybe even the two strings could be equal. Now, given two strings, our goal is to return the largest string x such that it divides both of these strings. Now, that doesn't necessarily mean that string 2 will divide string 1, because as we can see from this second example, we can't add this string twice to make this string, but there exists a substring ab which can make this string by adding it twice and can make this string by adding it 3 times. And also, don't let the problem trick you into assuming that string 1 is going to be longer than string 2. That's not necessarily going to be the case. They just tell us we're given two arbitrary strings. Now, there are many ways to solve this problem. Some can go really deep into the math, but I'll keep it pretty intuitive. You don't need super fancy math for my solution. So how can we even brute force this problem? Well, we can't just come up with our own random substring x. Let's try to take a substring from one of these two strings, such as this one. We can try a itself. We can try this one, its length of 1. Let's see if taking this and creating 4 copies of it, because this string is length 4, we have to create 4 copies of this. Does that create this string? Well, that would create a. That does not equal this string. Next, we could try the first 2 characters, which is of length 2. So how many times would we need to add it to make this string? Well, we would need to add it twice because this is of length 4. So this is kind of where the math intuition comes in. First of all, we're trying substrings from this one. Why did I choose this one? Well, because it's shorter than this one. We know that if we get all the way up until here, like this entire string, and we tried every previous substring and none of those worked, then creating a longer substring than this isn't going to work. That type of x added together will never create this string, because adding them together, we have to create this string and we have to create this string. So that's why we go with the smaller one, though it doesn't make a huge difference, I think. But more importantly, when we have a candidate x, we take the length of this candidate x, and we want to make sure that it is a factor of the length of this string. Because if it's not, then it will be impossible to create this string. Such as, for example, if we had this string of length 3, adding this together will never create a string of length 4. We will, though, be able to create a string of length 6, but that's not our goal here. We need an x that can create both of these strings. So another way to put it is when we have an x, we take that length of it, and we make sure that the length of this string, which let's call L1, we can mod it by this length. And when we mod it by this length, there should not be a remainder. So this should equal 0. If it's not equal to 0, we're not even going to try this candidate. And we want to make sure the same is true for the other string too. So we make sure to mod it by the length. If it's not equal to 0, then we don't do it. But if it is equal to 0, then we consider it. And how exactly do we consider it? Well, when we have a candidate like x, how many times do we have to add x together to create a string of length 4? Well, we can get that by taking 4 and dividing it by the length of this candidate, which is 2. That gives us 2 times. 2 times x is going to create this string. What about this guy? Well, it has a length of 6. So we take 6 divided by 2, which we get the 2 from the length of x, and then we get 3. So we need 3 copies of it to create this string. And then all we do is check, and then we just add it 2 times. Is it equal to this? And add it 3 times. Is it equal to this guy? If it is, then we return the result. One last thing we can do is that instead of going from smallest to largest, we can be a bit greedy and try the longest possible one first. Because remember, we're trying to find the largest x. So let's start being greedy. Let's start with the 4. Well, 4 doesn't divide with 6, so we can't even try it. Then we try 3. Well, it doesn't divide with 4. Then we try 2. Yes, it divides both of them, and it does create both of them, so that's what we would return immediately. So to analyze the time complexity quickly, since we're going to be iterating through the smaller string and checking in the worst case every substring of that, that's going to be our x candidate, we'll say that to do that, we're going to need to iterate between the minimum of m and n, where let's say m is the length of this guy and n is the length of this guy. And then every time we do that, in the worst case, given a candidate x, we're going to need to build this entire string, which is of length n, and we're going to need to build this entire string, which is of length m, and the time complexity to do that is going to be n plus m, and we multiply these two together because this is what we're going to call inside of that loop. So this is the overall time complexity. Now let's code it up. So we're going to start with the length of each substring, and then we're going to iterate through where L, this is an L, maybe I should make it capital, but I'll leave it lowercase for now. L is in the range of the minimum of length 1 and length 2. And then we want to check if is divisor. I'm going to create a helper function to do this, where the substring, we can pick either one, string 1 or string 2, because if it's a divisor of one, it has to be a divisor of the other. So we'll pick just arbitrarily starting with string 1, so a substring going from the beginning all the way to L. Oh, and I forgot, with our loop, we want to actually iterate not starting from 0, but we want to start at the number itself and then iterate down, going down -1 each time. But this substring, we picked it from string 1. We could have picked it from string 2, and the result would be the same, because remember, x, whatever it is, it has to go into both of the strings, and that's what we're going to check in our isDivisor function. Now, if this were to return true, that would mean we found our result, because we're doing this in a greedy way. So we would just return that string 1, going from the beginning up until L, and if we never find it out here, then we can just return an empty string. I think that's the default. Now, to actually define our helper function, let's call it isDivisor. It'll be given some length L. First, we want to check that L is a factor of the length of both strings. The easy way to check that is length 1 modded by L. So if this is non-zero, or if this is non-zero, then we know it's not a factor, because it has to be 0. So if it's not a factor of both of the strings, then we just return immediately false. We know it's not a divisor of both strings. But if it is, or at least the length of it is a divisor, then we want to actually try to build the string. But how do we build the string? Well, I'm going to create a couple variables, f1 and f2. These are going to be like the factors. I guess I should write out the entire variable, but I really hate writing out variables in Leetcode. So to get f1, we're just going to take the length of string 1 and divide it by L. We're doing integer division in Python because we need to round down. Well, this would never be a decimal anyway because we made sure that it is a factor, so I guess you don't really need that, but I'll leave it anyway. L2 divided by L. So these are going to be the factors. This is going to tell us how many times we have to multiply. So when we take string, that substring we were talking about, our candidate L, this is it. We're going to multiply that by f1, and we want to make sure that this is equal to string 1. And we also want to make sure that this is true for string 2. So here we just changed this to f2, and we changed this to string 2. You could say we need to change this to string 2. You could, it would work, but it'll work in both cases because remember, our candidate is going to be the same for both strings anyway.
way. And if both of these are true, we return true. If they're not, we return false. So we can literally just return this entire value. Oh, and quickly, I just noticed that here we're passing in the string. We don't want to do that. We want to pass in L itself. So this is the entire code. Let's run it to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If this was helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help.
If we want to take the really easy approach, we could probably use the Python command gcd. Well, I think that ruined the fun of the problem. So what I think a really good approach is if we go work backwards. We take the length of 1, length of 2, we get the length of string 1, and length of string 2. Okay. We have that. Then we have to get a for loop for L in range of min of length 1. So we're going all the way to length. So we take the minimum of both. Because we want whatever the smallest is. And we're going to 0, and we're starting to -1, right? We need some sort of helper function, make it easier just to read. We could do isDivisor. That'll take in the passing of L, and we just do that. If it is true, we just do string 1. We do however many we need of L. It won't really matter who we get it from because it's just like they technically are going to overlap anyway. String 1 is easier. This could also be string 2. Can also be string 2. Doesn't matter as much. Then we can do def isDivisor. Keep it very simple. So that takes in the L, the length. If length of 1% of length L does not equal 0, or length modulo 2% L does not equal 0, then we have to return false because it just means it doesn't work and there's a remainder. Else we can take the factor of 1, factor 2, which is just L len 1 divided by 2, and then length 2 divided by 1. Length 2 divided by L. And this is fine because it's already remainder, so it's a modulo. Return string 1 of L times factor 1 if it's equal to string 1, and then string 1 L times f2 equals string 2. And we can flip-flop string 1, string 2 around. It doesn't really matter. We're just trying to keep it very clean. It's just trying to keep it very similar because let's see now if it works. Unexpected indent. Oopsie. My fault, guys. Sorry about that. Unindent all this by 1. There we go. Oh. There we go. Run again. Can't multiply, so I got a float here. Maybe we do have to floor this just in case. Safe. Let's go. I think it should work. Cool. Number of 1 bits. Unsigned integer n, return the number of 1 bits in its binary representation. Huh. So we could just brute force it. Starting from left to right, just reading ints, but that would just be O of n. So there's definitely has to be a very fast solution for this. And realistically, it's Python.
Hey
is probably
everyone,
built on
welcome
focus.
back, and let's write some more neat code today. So today let's solve number of 1 bits. This is actually another blind 75 problem, and we've been tracking all blind 75 problems on this spreadsheet. The link to that will be in the description. Today we'll be doing number of 1 bits, one of the last problems remaining that we haven't done. And I also have a YouTube playlist for the blind 75 solutions. Link to that will also be in the description if you do want to take a look. Okay, so now let's get into it. We are told to write a function that takes in an unsigned integer, which isn't really important for this problem because all we want to do is count the number of 1 bits that it has. So the concept is pretty simple. So when you take a look at this number, we can see it's made up of zeros and ones, and we just want to count how many ones it has. Clearly it has 1, 2, 3, so we can return 3. But how can we actually count the bits? So obviously we need to do a little bit of bit manipulation. I'm going to be showing you 2 different solutions. One of the solutions, the second one, is going to be slightly faster if you're interested in it, and it's pretty difficult to come up with. But the first solution is a little bit more straightforward and is more doable. So like I said, the easiest way is just to count manually bit by bit, and then see which one of them are ones, and then increment our total, and then return the total. But let's see how we can actually accomplish that. So how do we know? Let's say we want to look at the first bit on the right side. How do we know if it's a 1 or a 0? Well, there's actually 2 different ways. One way is you can AND it with the integer 1. So since the integer 1 just has 1 here, and then the rest of them are zeros, when we do a logic AND operation, logic AND is basically taking the AND of every bit, but we know that every bit is going to be 0 when we take a logic AND. It's going to be 0 for every bit except for this one, which can either be 0 or 1. It'll be 1 if the bit in the input integer is 1, then we'll get a 1 in the output. If it's a 0 over here, then we'll get a 0 in the output. So that can tell us if there's a 1 here or a 0 here. Another way to do it is just to mod this by 2. Modding is basically taking this, dividing it by 2, and getting the remainder. Since this is the ones place, if we mod it by 2 and there is a 1 here, we'll get a 1 in the output. If there's a 0 here, we'll get a 0 in the output. So we have 2 different ways to do it. I think I'm going to stick with modding, but you can do it either way. Okay, so we have a way to detect if the first bit is a 1 or a 0. But what if we want to look at the next bit and the next bit and the next bit? How do we do that? Well, the easiest way would just be to take all the rest of the bits and then shift them to the right by 1. And luckily, most languages can natively support this, and it's a very efficient CPU operation. This is kind of the preferred way to usually do it in bit manipulation. Just shift every bit to the right by 1. We can achieve basically the exact same thing by taking this and then integer division by 2. Dividing it by 2 will basically shift all the bits to the right by 1 as well. But usually the bit shift operation is a little bit more efficient on your CPU, so that's what I'm going to prefer. So basically we're going to take these, shift them to the right. So now we're going to have a new integer 1, 0, 1. Again, we want to know if this bit is 1 or 0. We're going to mod it by 2. We're going to get another 1. So far we have counted two ones. And again, we would want to take these, shift them to the right. This time we get a 1, 0. We mod this by 2. We get a 0 in the output. That means there's a 0 here, so we don't add to our total this time. And lastly, we take this, shift it by 1. We get another. We basically get the integer 1. We mod it by 2. 1 divided by 2. The remainder after that is just 1. So we got our third 1. So our total so far is 3 ones that we counted. And lastly, we're going to take this and then shift it to the right. But what exactly is going to be remaining after we do that? Well, basically 0. And once we have a 0, it basically means we have all zeros, right? 32-bit integer will have 32 zeros, and that basically means that we can stop our algorithm now, and we're done. So we counted in total 3 ones, and that's what we can return. So once you're familiar with these bit operations, it's a pretty straightforward problem. So let's code up the first solution. Okay, so now let's code it up. I'm going to declare one variable for the result, which is basically the total count, the total number of ones that we're going to have, and I'm going to continue counting the ones while n is greater than 0, or in other words, while it's not equal to 0, which I can do just like this, and that'll work in most languages, I think. And then we want to know if the ones place is a 1 or a 0, so we can take n and mod it by 2. Now this will either be a 1 or this will be a 0. If it's a 1, then we want increment result. If it's a 0, we don't want to increment result. So in other words, we can just basically add this to our result itself. And then we don't want to forget to shift everything to the right by 1. So what we can do is set n equal to itself, bit shifted to the right by 1. After that, last thing we have to do is just return the result. So now let's run it to make sure that it works. And as you can see, it does work, and it is pretty efficient. But what exactly is the time complexity of the solution? Well, the good thing is that we're guaranteed that every input is going to be a 32-bit integer. So we know that while loop we had is going to run 32 times. So really the time complexity is big O of 32, which is constant time, right? No matter what the input is, the time complexity is not going to scale up. So basically the time complexity is constant. We can say it's big O of 1. And there's no real extra memory complexity needed as well. So it's also big O of 1. But a small downside of our solution is it has to count, it has to look at every bit, even the ones that aren't ones. So for example, what if we had a number like this? In this case, we're going to look at this bit first. Okay, it's a 1. We're done with that. Then we're going to look at this bit, this bit, this bit, this bit, every bit here, even though they're zeros, right? That kind of wastes time. Wouldn't it be convenient if we only had to look at the bits that were 1? That meaning our algorithm only has to run as many times as how many ones are actually in the input. And yes, there actually is a way we can do this, but it's not very easy to come up with. And it's probably not even worth coming up with because the time complexity will be the same. It'll still be constant time and constant space. But it might be good to just, get really good at your bit manipulation tricks and stuff, and maybe you'll see this in an interview. So the main operation we're going to be doing in our while loop with this trick is basically taking n and setting it equal to n, logic ANDed with n minus 1. And this is what we're going to do in every iteration of a loop, and each time we do that, we're going to increment our results by 1. But the question is, why does this work? First, let's see what will happen. So, okay, so what's going to happen? Let's take this integer and subtract 1 from it, right? That's what we're going to do over here. So n minus 1, which is going to be this. And now we're going to logic AND them together. What are we going to get when we do that? We're basically going to be removing this, right? We're going to get n minus 1 itself. And we're also going to increment our result by 1 now, regardless of what the output happens to be. Okay, so now our n value is going to be set to this. Okay, so now our new value is going to be 1, 0, 0, and all zeros. Okay, now we're going to take this number and subtract 1 from it. What is that going to look like in binary? Well, it's going to be 0, 1, 1, 1, 1, 1, 1, 1. Okay, and now we are going to logic AND these two together. What's that going to look like? Well, we're logic ANDing every bit. This one is going to turn into 0 now. And the rest of these are also going to be 0. Even though we have ones in the bottom number, we have all zeros in the number above. So now we're actually done with our entire loop. Now we have all zeros. We incremented our result by 2, so now our result is 2, and then we return, right? Which makes sense because when you look at the original number we started with, yes, it did have 2 ones in it. But how did this algorithm work? Well, it's actually really simple, but it's definitely not easy to come up with. What we're doing when we're subtracting 1 from itself is we're basically getting rid of a bit, right? When we took this number and subtracted 1 from it, we got rid of this 1 bit, right? And remember, we're counting 1 bits. So when we did that, we increment our result by 1. But then why did we logic AND it together with itself? Well, basically, since the rest of the numbers stayed the same, and we took this 1 away here, and then we logic AND them together, we're basically removing that 1 bit. So then when we logic AND these two together, you can see that the 1 bit was removed, but the rest of the number stayed the exact same on the left. Okay, that works. But what about this number, right? Then we were left with this, and then we subtracted 1 from it. Then what did we do? Well, again, when we subtracted 1 from it, we basically got rid of the next 1 bit, right? You can see that when we subtracted 1 from it,
this is what the number looked like. We got rid of this 1 bit, but we introduced a bunch of other 1 bits. But these are all okay because we know they're going to be, and any 1 bits that we introduce are going to be on the right side. And we know that if we just deleted this one, it was the rightmost 1 bit that we had. So any ones that are introduced to the right side won't matter in this number. This is n minus 1, by the way. Any ones here won't matter because remember, every time we do that, we're logic anding them together. We're logic anding n with n minus 1. So these are all going to cancel out, and this is going to cancel out as well, the position where we remove the 1 bit. So basically what we're doing here is we're skipping all the zeros in between. We're basically allowing ourselves to run the loop as many times as basically as many 1 bits exist in the input integer. It's kind of a really weird trick, but it definitely works, and it makes sense why it works. Now we can code it up, and it's pretty simple. So you can see that this was our original solution, and we only have to modify this a little bit. So what we're going to do is get rid of this line, and instead of incrementing our result by n mod 2, we're actually going to increment our result by 1 each time, because each time we increment this, we are going to be setting n equal to n anded with n minus 1. So we're going to be counting the number of 1 bits exactly. And this line can actually be slightly shortened by doing this in most languages. And yeah, so this is about as efficient as we can get. We won't run any extra iterations of this loop when we have zeros, so let's run it to make sure that it works. Ooh. And you can see, yes, on the left side it works. Yeah, the runtime is about the same because it's still the same exact big O time complexity, but I hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.
So literally a simple approach was literally just doing result, which is equal to 0 for I in range 32 because we're going to 32. If 1 I and n, so there's still an end, result plus equals 1, and we just return result. Very simple approach. Nice. I mean, that's just a shift bit to should be my 1. But there's a very cool approach. I think we can do this way even way cooler. You just skip a lot more. While n does exist, we can do an and switch that would compare everything. Result plus equals 1, and we just return result. Bam. This would be way better of an approach. Technically same, because on high level it's just 32, so it doesn't really matter as much. Bam, 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 bam! We're at what, 36?
Things are about to get
my feet. Time to get this shit done, baby. Okay.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve design, add, and search words data structure. So this is another problem from the blind 75 Leetcode problems list. So this is the spreadsheet I've been using to track which videos we've uploaded for those 75 problems. You can see that most of the solutions have already been updated, and today we are working on this problem, a tree problem, add and search word. So basically another day, another problem from this Leetcode blind 75 list. The link to this sheet will be in the description if you do want to take a look. So basically we're designing a data structure to efficiently solve this problem of basically adding words. We're taking new words, adding them to the data structure, and also we're being given words and we want to search to see if those words match any previously added words to our data structure. So we only need to support 3 functions for this data structure. One is just going to be the constructor that's going to initialize the object. One is going to be adding a word, and that one is pretty self-explanatory. So we're just given a string, a word, and then we're adding it to the data structure. Now this word could only consist of lowercase characters from lowercase a to lowercase z. And the third one is going to be the one where the bulk of the algorithm is going to be contained. So this is going to be searching words. So we're searching a word, and the word can contain any character from lowercase a to lowercase z, but there's one additional character it could contain, a dot character. And what we're told is that the dot character is actually like a wildcard. It can basically match any character in the string. So for example, let's say in our word list so far, let's say we had just a string a, b, right? So this is what we have so far, and we're trying to search dot b. So basically, would this
search match any words that contain so far in our data structure? The answer is yes, because the dot would match any first character, right? So we basically match this lowercase a, and then we do have an additional b, which matches the second character in the string. So a dot matches any character. That's what's going to be tricky for us to implement. Now, the brute force way to solve this problem is pretty simple, right? We would basically have a list of words, and then just for every search, we would just say, okay, does this search match any of the words in the input list? Now, that's not going to be super efficient. A more efficient solution is going to require a trie data structure, aka a prefix tree. So this is what we're going to be using to solve this problem efficiently. I will say, if you've never heard of this data structure or you've never implemented it before, you basically don't have a chance of solving this problem efficiently. But if you have heard of this data structure, it's pretty intuitive why this data structure is used in this problem. Basically, a prefix tree, right? So for example, if we were searching b dot dot, we would want to first find all words that start with the character b, and then check, are any of them of length 2, because the remaining portion of this can match any string of length 2. So a trie is basically a tree that has some kind of root node, and each node can have up to 26 children in this example, because we have lowercase characters from a to z. So basically, each node is going to represent a single character, right? And then each node could have up to 26 additional children. And basically, a word in this case, for example, this is a. If I had a b here and then another c, this is going to be a single word, right? And so if we inserted the word, let's say we added the word ABC into our trie, this is basically how it would look like. Now, one additional thing we have to say is for a particular node such as c, we have to say this is the end of the word, right? Because what we're trying to say is we did not add the word a, we did not add the word ab, we've only added the word abc, so we have to designate that this is the last character. Now, if we added another word, for example, ab, what we're going to do, we're not just going to repeat that. We're not just going to say, okay, now there's going to be a lowercase a here, then there's going to be a lowercase b. Notice how we already have those characters available to us. We're going to reuse these characters. So instead, we would do this word, we would say, okay, let's add an a. So let's start the root, add an a. We see there's already an a that exists. Then we'd say, okay, from here, let's add a b. We see that a b already exists. So once we get to the end of the word, right, that was the last character, then we just say, okay, designate this as an additional end of the word. So now we have two words along this path. We have one word ab, we have another word abc. Notice how all words starting with an a are going to be here, right? We could have other words, maybe at or something, right? And other words as well, right? Basically, all words that start with a are going to be here. That's what makes this efficient. That's why this is called a prefix tree, because let's say we wanted all words starting with, let's say we were searching something like this, right? We're searching ab dot dot dot. So we want all words, for example, or even one word of length 5 that starts with ab. Then we go, okay, let's find a, then find b right here, and then we go through all possible children that it has, right, in the tree. We would do a brute force depth first search, backtracking type approach, and then we'd get a word. We would try to find a word like this one. So with that being said, let's run through the example. You can see at the above, the first word that we're going to be adding is bad. So let's add a character for b. Let's add a child for this a. Let's add a child for it d. So now we have inserted the word bad. We do want to designate this as the end of a word, so I'll just mark it blue, but in our code, obviously, we're going to do something different. Next, we're adding another word, dad. So we have to start along a different path because these two words have a different prefix. One starts with a b, one starts with a d. So let's additionally add a and additionally add d. Once again, designating this as the end of a word. We're going to add one last word before we start searching. This one's going to be mad, so we don't already have an m, so we do have to insert that, and then we have to insert a and then d. Of course, this is going to be the end of a word. So far we have 3 words. All of them end with a d, but all three of them have different prefixes. That's why they're along different paths. Now let's get to the searching part, the interesting part. So we're going to search for a word pad. Now, so what we're going to do is we're going to start at the beginning, right? Are there any words pad in this? So first we're going to try, are there any p's? We're going to look, is there a p? We don't see any, right? We only have b, d, and m, so we don't have any words starting with a p. That means immediately we know false. Pad does not exist in our input. That's why in the output over here, you can see false is what's returned. Next, we're searching another word. That word is going to be bad. So we're going to start at the root and see, are there any b's? We're going to see that, yes, we do have a b over here. The next character in the string is a. So does this b have a child a? Yes, it does. It has an a over here. The last character is a d. Does this a have a child d? Yes, it does. It's over here. Now, yes, we found the characters we needed, but now lastly, we have to say, okay, the last character that in the searching word is d. Is this in our trie? Is this designated as the end of a word? Since it's marked blue, it is. Therefore, we're going to return true for this input searching word. And you can see that's what's written in the output. This returns true. Let's go through the last 2 search examples. So in this example, we have dot a d. So what does that mean? Remember, the dot character means we can match any character. So we're going to start at the root, and we're going to go down all 3 paths, or literally any of the paths. And to do that, we're going to have to use depth first search, or basically a backtracking approach, right? And remember, we're only looking for one word that matches this, right? So let's say the first path we decide to go down is this one, right? So this is a b, and we're allowed to use a b because the dot matches any character. So this matches so far, right? Next, we're at the next character a. Does this path have a child a? Yes, it does. So we found another match. Next, we're looking for a d. Does this have a child d? Yes, it does. And it's designated as the end of a word. So in this case, we found one word that matches this, and that's all we need. We just need one word. So we are going to return true, and you can see that up above. Now, if this one did not match, for example, if this wasn't designated as the end of a word, or maybe this was instead an x character, we would say, okay, we didn't find a match down this path, but it doesn't matter because remember, the dot matches any character. So we don't have to go down this path. Let's try going down this path, right? And we would do the same thing. We'd say, okay, we have an a, we have a d. That means we found a match. That means we can return true. And you can see that this is not going to be super efficient, right? We would have to go through every single character that's in our trie decision tree. But it's still more efficient than a brute force approach, especially for this last example. So we're doing one last search, and in this search, we start with a b, but then we have 2 dot characters. And the reason this is more efficient with a trie rather than just brute forcing every list, because this at least tells us, okay, we're starting with a b. So what we're going to do in our trie decision trees, we're going to say, okay, every other word that starts with any other character than a b, we're not going to consider them. And we have a pretty small trie right now, but it's possible we have a really big one, right? So what this does for us is it eliminates a lot of the possibilities. We say, okay, at least we know we're starting with a b, and yes, we did find a matching b. So we can go down this path. Now we get to the brute force portion where we have a dot, right? So basically, in this case, it's simple because we only have one child, but maybe we have multiple, and then we have to go down all of those paths. But in this case, it's simple, right? Let's just check, do we have any characters that go below it? Yes, any character will match this first dot. Now we're looking for another second dot. Do we have any characters that match it? Yes, we have a d, and it's the end of a word. So yes, in this case, we also found a match, so we can return true, just like we have up above. So once you can kind of understand this visual example, it's not super hard. Now it's time to actually implement the code, and I'll admit that it's actually a little tricky, but I'll try to guide you through it. So one thing I like to do for trie problems is just define a trie node, because it's going to have a couple variables. So in the constructor, we're basically going to initialize 2 fields. So for this trie node, we are going to have a list of children. Now I'm going to use a hash map for that. So basically what I'm going to say is for each character, we're going to say something like, A is mapped to a try node, and we could possibly do that for every lowercase character from A to Z. And for every character, we also need to designate if it's the end of a word. So I'm just going to use a Boolean for that, call it word, and initially we'll set it to false. And so basically the only thing we need to do for the constructor of the word dictionary is just define a root. So let's call it root, and it'll just be a try node. So initially you can see that we don't have any characters inserted, right? We just have an initial empty try node. It doesn't have any children, so no characters are inserted. Next, we are going to do the add word portion. This portion isn't too difficult. So what we're going to do is we'll set current equal to what our root is. So self.root is where we're going to start, and what we're going to do is basically go through every single character in the word. And what we're going to do is we're going to check if this character is not already inserted, because it's possible this character could already be inserted in the try. So we're going to check if C is not in current.children of the current node's children. If C is not in there, then we need to obviously insert it. Right? So what we would do is say current.children of C is going to be a new try node, where we inserted a try node corresponding to the character C. And then of course what we're going to do is we're going to update our current pointer to this new try node. If it didn't already exist, that means we just created it. If it did already exist, then we just shift it over to it, right? What we're ultimately trying to do is insert every character from this word into our try. And once that's been completed, what we're going to do at the end is say, okay, current.word is now going to be set to true. So we have created the characters and designated this as a word. Okay, now for the actual meat and potatoes of this problem. And this part is actually going to be recursive, and let me show you why before we actually start doing the recursive portion. So this is going to start similar to what we had before, right? So current is going to be initially set to, let's say, self.root, right? And then what we would want to do is go through every single character in the word. In this case, I'm actually going to use the index of the word, and you'll see why in a moment. So for I in range, length of the word, and then we're going to get the character at position I, so word of I. And so remember, this character could be any character from A to Z, in which case the problem would be straightforward, right? We would just search our try and see does this character already exist, and then we'd continue. If it doesn't already exist, then we would return false. But we know this character could actually be a dot character. That's what's going to make this tricky. So if C equals a dot character. The else condition is if it is a regular character. Now let's start with the else case because it's a little more simple. So if C is just a regular character, what are we going to do? We're going to check if C is not in current.children. That means this character does not exist. We needed this character to exist. We're searching for this word, but this character does not exist. So what do we do then? Well, simply we can just return false. That means we know for sure this word does not exist. If it does exist, then obviously we're going to shift our current pointer to that node. So we're going to go to current.children at character C. And then we would just continue our algorithm, right? But in this case, it's going to be a little bit more tricky because remember, if the character is a dot, that means potentially we're going down 26 different paths because this dot could match any of the 26 characters. And we can't really do that iteratively very easily, right? We are going to use backtracking or recursion to help us do that. So for example, let's say we had a string like .ab. What we would want to do then is say, okay, dot, it could match any of the possible characters. So what we would say then is we would go through for every child in current.children .values, because remember for current.children that's a hash map, and then we want only the values because those are going to be the actual children. So because we know the dot could match any character, so for this dot we would basically match every single character, and then we'd say okay, for each of these we want to do the recursion on it. So we want to do the depth first search on this, and when we're actually doing that depth first search, it could just be an iterative matching. So what I'm trying to get at is that this entire thing that we just wrote is the recursive function. This is the depth first search, right? We have the iterative portion here where we don't have a dot, and we have the recursive portion over here where we do have a dot. So let's wrap this entire thing inside of a depth first search function, depth first search DFS, and so let's just tab it over. So now let's think about it. When we're doing our depth first search, what are we going to pass in? Well, we want to know what's the remaining portion of the word that we are trying to match, right? So we would want to pass in the index. So let's call that J. We're passing the starting index J, right? And the other thing we're passing is what's the current root or the current node in our try that we're at. So in this case, depending on which one of these we're iterating through, we're going to pass in that child node, right? So that's what the node that we're going to be passing in, whatever child that is. So that's how we're going to call DFS. So let's define that up above. So J is going to be the index parameter, and let's call root what the node that we're passing in is. So okay, so current is, instead of being called self.root, it's actually going to be initialized to the root that we end up passing in. And okay, so here I passed in J, but what we would actually pass in is going to be I. Actually, not just I, but I plus 1 because we're going down a child. So we're going to pass in I plus 1 as the index of the character that we're looking for, right? Because what we're saying is we're skipping the dot, so we're going to have to increment I plus 1. And this function is going to return a Boolean. So if this function ends up returning true, that means we found one path that matches. And remember, if we find a path that matches, we return true immediately. We're done. We don't have to do anything else. If we don't find a path, we're going to keep going down all possible paths until we do. If we never find a true, if we never find a match, then we're going to return false. Oh, and one more thing. So initially up above, we said I is going to go through range of the length of the word, but we know we could be starting at a different position. Here, we're always going to start at 0. We don't want to do that. We always want to start at J, whatever it happens to be. So that is the main recursive portion. And the last thing is, let's say we were given a word ABC, and let's say we found a match, right? We didn't have any dots in here. What would that do? Well, we'd go through the for loop. We'd always execute the else condition, and we would always find the current node, and then the entire loop would be finished. Then what would we want to return out here? Well, we would want to return whatever current happens to be. So if current.word is true, then we would return true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm. The last thing that we want to do is actually call this depth first search function, right? So what are the parameters that we're going to give it? Well, we're always going to start at index 0 because we're going to start at the beginning of the word, so we can pass in 0 for J. And we're always going to start at the root node of our try, so we can pass in self.root as the root node, and then we would just want to return the result that this DFS function returns. So as you can see, this function did work, and it does work pretty efficiently. So if you didn't already know what a try was, I hope that you learned that today. So this is the entire code. And if you did already know what a try was, I hope that you learned a new application of it. So I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Nice. Alright guys, I understand it generally pretty well. The brute force way would always be adding it. We would check to see. So I'm looking at it right now. So to make it very simple, we can add a try node here. Try node class, and I want this to maintain all the information. Self. Sorry about that. Self. Now what I'm thinking is we have children. And for this we can have a dictionary or a set. Whatever. Just usually it's faster just in case. A list could work, but I think a dictionary makes more sense, especially with the way we want to go about doing this word. And if it's a word, false. I'm going to notify you that it's a word. Now, obviously, we want to initialize the word dictionary. We can make this the root, so self.root, and we'll always initialize an empty try node. Okay, so we got the first part set. Now we need to add a word. And this here, as you can see, it takes in a word string and it returns nothing. So we're safe for that. So right now we need something to keep track of the current thing we're at. So current, and we can do self.root, right? We're initializing it as the root. Now we get the word. We want the character, the letter. So for letter and word. And now we need to see if it's already in it or not already in it. So if it's already in it, we should be fine. So we want to more be worried about if it's not in it. So if character, if letter not in the current dot children. And the children right here is here. Current dot children. Then we're going to add this. So current dot children. Then letter. We associate that letter with a try node. Okay? Then current is equal to the current dot children with this current letter. So now we should be here at the letter itself. And then the word means it's true because we actually found that word. So that means we found the word exists, and we have it in there. Okay. Because it'll keep iterating through the letter and we add a final at the end. Cool. I think this should work. We would need a test case to double check this, but I think we'll keep it safe for now. It loops through each letter, adds it, and bam. Now we need our search here. So for our search, we got to not only just worry about finding the word, we need to also handle worrying about with the period before and after. Now there could be a simple brute force way to do about doing it, but since we have some sort of tree going on here, there's definitely some advantage we can do with a depth first search. And I think we could take that approach. So I know we need some sort of DFS, short for depth first search. Some sort of variable here, and we need to take in the root. The root would just be the word, right? Let's just do J root, okay? And we take... I'm thinking right now, we have the depth first search. We need to then just take some sort of current, which is equal to the root, so we know where we're tracking. Now, we need to look for the word. So we need some sort of for loop of some sort. I might have to take a recursive approach for this DFS as we are going to be going through something. So maybe for I in the range of some index, some passing. So from J to the length of the word. That makes sense. Okay. So we start at J and go to the length of the word. And then now we have char character, which is equal to word I. Okay. Now we have the word I index. If the character is equal to period, this means our wildcard. The wildcard. Just keep that in mind. So now this is right. Now we need to then somehow look at each value in this list of try nodes here, this dictionary. So maybe something, a for loop of some sort, for child in current, and then our children, which is the thing, and we need their values, as it's the key is the letter, the values, key value pair. The letter is the key, the value is the node. Yeah. Bam. Then we can do our recursive DFS call. If DFS I child. And we need to add one here because this is an additional for loop here, right? This is an additional one because we need something to iterate through to keep continuing. We need to be one more ahead because we're starting at I. We're iterating for letters. Okay. And if this is true, if it somehow goes through all this, that means the word, there's a word that exists, so we can just return true. There has to be a word that exists for it. But if it doesn't return true, then it has to return false. Okay. Now, else. This is just the word. So we got the hard part done. If character not in current dot children, we can literally just return false. Else. Sorry. Else we have. Let me just write. We don't need else. We can just do current equals current children dot c, and then the final return of this DFS would be return current dot word. There we go. And then we just need something to call this, so we just call return DFS starting at the root and then self dot root, just being passed it, starting at the beginning. Let's test it to double check. Oh, sorry, it's supposed to be character here. Let's go right here. Ooh, nice. Okay. Looking good. Let's see how we passed all our test cases. Ooh. Where'd I mess up here? Self.children, self.word equal false. Self-root try node, add word, the current for letter in word, if letter not in current child, current children, letter equals try node. The current is equal to current dot children dot letter, and then the current word equals true. Yep. We got our def search, our DFS, the current is equal to root. For I in range J, the length of word, we have character equals word I, if character equals period. For child in current children dot values, if DFS I plus 1 comma child return true, else you return false. Oh, that's where I messed up, guys. I returned false for the first one. I indented that too hard. There we go. Good job, guys. Let's get it. Nice. Pretty happy with this. Nice. Cool. Another graphing problem. In an alien language, surprisingly, they also use English lowercase letters, but possibly in a different order. The order of the alphabet is some permutation of lowercase letters. Given a sequence of words written in an alien language and order of the alphabet, return true if and only if the given words are sorted lexicographically in this alien language. For example, input dog, dis, dag, dis, dog. Order. Okay, explanation. The first characters of the string are the same. D, A, I, O. Follows this given order, which makes given string follow sorted lexicographically. D, A, I, A, O. Like it's just in order. First four characters are both remote. Oh, okay, I see. So we need to compare each individual letter, each individual thing. So I could see a brute force approach where we just do the order is passed in. Okay, so we're comparing it against the order. I see. Oh, I get it. Okay. I don't want to do a symbol. That's a sorting, comparison. I gotta take a fat shit, boys. Fat shit.
To the word conversation again. What makes a good conversation? Active listening, critical thinking, and bringing value to that conversation. After you've gotten
I'm super excited, guys. Let's get back to it. Ooh, I'm really, really excited. Ooh. Let's go for it. I'm thinking of this problem.
Hey everyone, welcome back, and let's write some more neat code today. So today, verified end of the string. So it's basically, hey everyone, welcome back, and let's write some more neat code today. So today, let's solve Facebook's most asked question of 2021, verifying an alien dictionary. And the funny thing is, I think this was also Facebook's most asked question of 2020, so I guess they really like to reuse questions. But let's get into the problem. And you might recognize that we've actually solved a very similar problem to this as before. We've solved the alien dictionary problem, which was actually a very hard problem. And the good news is that this problem is a lot easier, and this problem itself is actually a sub-problem of that alien dictionary problem. So if you've solved that before, you'll definitely know how to solve this. If you haven't solved that before, I think that other problem is a really good follow-up problem to this problem. And I will probably link it below if you want to take a look at the solution for that problem as well. But for this, the premise of the problem is pretty similar. So we're given an alien language that happens to use all 26 lowercase English letters. But the difference is that in the alien dictionary language, these 26 English characters, A, B, C, etc., right, they could be in a different order than the A through Z order that we are all familiar with. The alien order could be some permutation of the ABC order. And we are given a sequence of words of the alien language that are or should be in sorted order based on that alien language. And we want to return true if these words are actually sorted based on the alien language, and we want to return false if they're not sorted based on the alien language. And we are actually given what the alien ordering happens to be. So instead of A, B, C, D, all the way to Z, the alien language in this problem is actually in a different order. You can see it's H, L, A, B, etc., right? So it's a different order than we are familiar with. And we're also given this list of words that should be sorted in order. Now, obviously, in real English, these two words are sorted. How do we know that hello comes before Leetcode in English order? Because we look at the first character, right? We compare character by character. These two characters are different, right? The first different characters are how we compare two words, right? Since these characters are different, we want to know, okay, which one of these characters comes first? Of course, we know H is less than L in English order, right? H comes before L in the English language, right? So, of course, in real English, H, hello, is going to come before Leetcode. Is that also true in the alien language? Well, let's take a look. So we're looking for characters H and L. We can see that H is actually the first character in the alien language, and L is the second character in the alien language. So yes, even in this alien language, these two words are sorted correctly, so we return true. Of course, we can verify the alien dictionary based on the first differing character, but suppose we were given two words such as these words. We compare character by character, right? We were looking for the first differing character. So we look at the first characters, they're both H, so they're not different. So we're going to look for the next character that happens to actually be different. We find an E and an E, so again, we shift. Now, notice how one word was a prefix of the other, because we reached the end of one string, but we did not reach the end of the other string. So in this case, this word was a prefix of the other word. So then the question becomes, which one of these words is supposed to go first? Basically, it works the same way as in English. If one of the words happens to be a prefix of the other word, then the smaller word goes first. So therefore, this is a true alien dictionary, right? This is verified as true. But if it was the opposite, if we had, he come after hello, that would be wrong, right? Because we reached the end of the second string, but then there's still some characters left in the first string, so that this would basically be false, right? We can't have something like that happen. And if you kind of want to know why, it's basically, okay, we reached the end of the string, so it's basically an empty character, and here we have an L, so what is smaller? Technically, an empty character, aka a space or whatever you want to call it, is always going to be smaller than any real character, so that's why he comes before hello. So those are the only two rules that you really have to note to verify this alien dictionary. So now we can finally get into the code. Now let's get into the code. You can see that I basically summarized the two rules that we have up above. Basically, we're looking for the first differing character. If we can find it, if we can't find the first differing character, that means one word is a prefix of the other. If word A is a prefix of word B, then word A must come before word B, so word B must come after word A. So the first thing we want to do is actually get the index of every single character and put it in like a hash map or something, so that's what I'm going to be doing. So I'm going to go through for every index character pair in our input order string. In Python, you can enumerate it to get the index and the character at the same time. We're going to use the character as a key, and we're going to use the index as the value. So that's pretty much what I'm doing with this one line. So then when we do find the first differing characters, we'll be able to compare which one actually comes first in the alien dictionary. So then we just need to go through every pair of words in our words array and make sure that every pair of words is in order. So we can do that pretty simply by going through every single word, the length of words -1, because we're going to be comparing every single pair, every adjacent pair, so we can get those words now, word 1 and word 2 that we're going to be comparing. Word 1 is going to be the word at index I, word 2 is going to be the word at index I plus 1. And now we just want to go through character by character in the words. We're going to go in range of length of word 1 because if the words happen to be similar, or if word 1 is a prefix of word 2, then we can reach the end of word 1 and we'll verify that it was in correct order. But if we reach the end of word 2 before we reach the end of word 1, in which case this would happen, right? The J happened to be the length of word 2, but somehow we were still inbounds for word 1. That means that word 2 is a prefix of word 1, which is not allowed. So if we ever reach this condition, that means we have determined that this is not verified. We have to return false in this case. We reach the end of word 2 before we reach the end of word 1, and we didn't encounter any differing characters, and word 2 obviously comes after word 1. You can see that I plus 1. So in that case, we would have to return false. If we don't reach that case, we're going to be looking for the first differing character. So let's go character by character. If the character in word 1 is not equal to the character in word 2, then we have found our first differing character. Now we just want to verify that the character in word 1 comes before the character in word 2 in our order index map. So if that's not the case, basically, if order index of word 2, the character in word 2, happens to be less than the order index of the character in word 1, that means we do not have a verified word list, right? Because word 2 is supposed to be greater than word 1. The character in word 2 is supposed to be greater than the character in word 1. If we have the opposite, that means that this is not verified. That means we have to return false. But if the opposite is true, that means these two words are verified. We're not going to return true quite yet because we might still have some words to iterate through, but at the very least, we can go ahead and break out of this for loop, meaning we can stop comparing these two words. We already found the first differing character, and it happened to be valid, so we don't have to continue. And if we end up going through every single adjacent pair of words in our words list, and we never return false, either by finding differing characters or by finding some prefix that was out of order, then we can go ahead and once the loop is done executing, we can go ahead and return true all the way outside of our for loop. And of course, I always have typos. For some reason, I took the length of words, but we actually want to take the length of words. That's what it's actually called. And then that gives us the optimal solution. As you can see, it runs pretty efficiently. Basically, the overall time complexity is the total number of words, the total number of characters in all words in the input. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Okay.
Had a chance to think, almost on their own. And today, that's what happened.
Huh.
Young man, you too can become a hero.
at this problem.
I just have to hold on and keep going. I have a chance here. I have to reach out and take it. The only way to stay ahead is to take another leap.
So a very fast way I think we can go about doing this is I think we can compare the words to themselves, to each other. So we have to obviously have a dictionary, which would be, we have to take a dictionary for the word order. That way we can have a very fast search comparison. We could try to sort it, but I think sorting it would take a little too long. Maybe n times m, where n is the number of words, and m is the average length of the words, which would be really bad for runtime. And multiply by log n, as the size would obviously get smaller, but the space would get really bad because we'd have to store this ordered words. There definitely has to be a faster approach where we can just do, where we just compare them themselves directly. So I'm thinking a very faster approach would be maybe comparing them to each other. As if we know one of them's out of order, we're already done. We can just return false. But if none of them are out of order, we can just return true. Okay. So we can do order underscore index, which is equal to, which we would now need, what? Which would have to represent a key map value pair. So since, you know, in the thing we're going to be comparing, we're going to get the letter first, so we probably want the character. We can probably just use letter. We want letter and then index value for index and letter in the enumerate
This
we're
message
going
is
to enumerate
brought to
order.
you by Apple Card.
Cool.
Get 3% daily cash
Okay.
back when you buy
Now
an
for
iPhone using Apple Card
I
at Apple.
in the
Subject to credit
range
approval.
of
Apple Card
the
issued
length
by
of words
Goldman
minus
Sachs Bank
1.
USA, Salt Lake City branch.
So we're just going to
Terms
keep
and
living
more
through
at
every single word
applecard.com.
letter in there.
For a limited time at McDonald's, get a Big Mac extra value meal.
And because it's going
That
on,
means
it
2 all-beef patties, special sauce,
should already be
cheese,
ordered.
pickles, onions on a sesame seed bun, and medium fries, and a drink. We may need to change that jingle.
Prices and participation may vary.
So we should be fine with this. Iterates to every letter. We're just going to take word 1, word 2, which is equal to words, the first one, and then just words, the second one. Just generally keep us safe. So we're looking at the constraints here. Length of the letters are max 20, the length of words is going to be max 100. Now for J in range, like the word 1. Okay. If J is equal to the length of word 2, we know it's already out of order, so we can just return false because the prefix doesn't need to always be in the front. Now we do if word 1 J does not equal word 2 J. And so now we're checking to see if they're not equal. If the order index, the order index, which is our dictionary, we could do word 1 J, see where there it is. If the word 1 is greater than order index for word 2 J, then that means we can just return false because if there's an error. We can just break out of it, and that means we can just break out of it again. Uh-oh. If it doesn't return, we can just break, we can just return true. Correct. Sorry, this needs to be all the way out here. There we go.
secure the future. By defeating all that threatens it. By winning the battles that will shape what's to come. Together. We are Marines.
Cool.
We were made for this.
Advanced scrap. Network delay. You were given a network of n directed nodes labeled from 1 to n. You were given, also given times a list of directed edges where times I, ui, vi, ti. ui is the source node, measured from 1 to n. vi is a target node, a number. ti. Okay. Okay, so we know there's some sort of direction here as well. Start at node 4. Oh, we started node 1. Bam, bam. So, I'm thinking we take some sort of depth first search, maybe. Thought so. Ugh.
Hey everyone, welcome back, and let's write some more neat code today. So today, let's solve network delay time. The reason I'm solving this problem is because it's a rare problem that you actually have to use Dijkstra's, however you pronounce that name, this algorithm. It's the shortest path algorithm. It's not super common on Leetcode, but I think it's a really cool problem to solve, a cool algorithm to implement. So obviously this is a graph problem. We're given a network of n nodes labeled from 1 to n, and we're also given a list of times. The times are going to be our edges, so it's going to be directed edges. So a time is a triple value. The first value in this triple is going to be the source node. So for example, this node 2. The second value is going to be the target node. So for example, 1 is this node, and the reason it's a target is we can see that there is an outgoing edge going from 2 to the 1. So every edge is going to be directed, right? We can see there's a directed edge there, a directed edge here. The third value, and this is also pretty important for this algorithm, is the weight of the edge. In the context of this problem, the 1 basically just means the amount of time it's going to take for us to go from here to this node, right? But this is the weight of the edge. So we're given a original node k. So this is our starting point. The node k is going to be the starting point. So for example, in this problem, in this graph, we're given k equals 2. That means this is the starting point for us. What we want to do in this problem is, starting at 2, how long would it take for us to visit every single node? Basically, if we sent a signal from here in every direction, so in this direction and in this direction, how long would it take for that signal to reach every single node? Now, if it's not possible, for example, in this case it is possible, but what if we had a 5th node over here that's just not connected to these 4 nodes over here? Then it would be impossible for this node to send a signal here. In that case, we're simply going to return -1 because it's not possible. But what about in this problem, because it is possible? How long is it going to take? That's the only question. Now, looking at the picture, it's pretty obvious. So starting at 2, how long is it going to take for this to reach a signal? It's going to take 1, right? Because the weight of the edge is 1. How long is it going to take for this node to get the signal? Also 1, because the weight of the edge is 1. So now we're over here. Let me just change the color to make it a little bit better. By the way, this was the original node. How long did it take this node to get the signal? Technically 0, right? Because it's the one sending the signal. How long did it take this 3 to reach the signal? 1. How long did it take this to reach the signal? 1. Now we're going to continue going. From this 3, we know that this 1 doesn't have any more nodes that it can send the signal to, but this 3 does. It has a node over here, 4, right? Now, how long is it going to take this 4 to reach the signal? Well, the weight of the edge is 1. So does that mean it's going to take the 4 1 second or whatever our time unit is to reach this? No, because we have to add the 1 from over here, right? Remember, our signal first started over here, then it traveled over here with 1, then it's going to travel again over here with 1. So in total, once we have visited this node, it's going to have taken 2 units of time to reach it. Now, after this node gets the signal, that means everybody has gotten the signal. How long did it take? What's the largest value we have? It took this one, right? This one took 2 seconds or whatever. So therefore, we're going to return 2 because after 2 units of time, every node has received the signal. So our output value in this case is going to be 2. Now, from looking at this example that we ran through, you might be able to tell that Dijkstra's algorithm is actually a breadth first search algorithm that I'm going to show you the general idea of. But the one difference about regular breadth first search is this algorithm actually uses a minimum heap, aka a priority queue. So we're going to be needing this data structure. It's not a super common data structure, but it is needed for this graph algorithm. Let me show you the actual algorithm. After that, we're going to jump into the code. So in case you want to Google this algorithm or do some more research, it is called Dijkstra's algorithm. It is a shortest path graph algorithm, and it's pretty common. You have probably learned it in school if you study CS. And what it does is, in this case, let's say our source or our starting
starting point is this node, the value 1, what it does is for every other node, it basically tells you the shortest path, right? So for example, 3, what's the length of the shortest path to this node? Well, directly from 1 to 3, it takes 1, so 1 is going to be the shortest path for this node. What about this 2 node? What's the shortest path to this node, right? With this, it's pretty obvious because there's only one way to get here anyway, but take a look at this node. There's 2 different ways to get there. Now, is this the shortest path? It's the obvious path, right? It's just 1 node away, but the edge has a weight of 4. That's a problem because take a look at the second path that we can do. We can go to 3, right, over here, then we can go to the 4, and then we can get to the 2, right? That took 3 edges, didn't it? That took 1 edge, 2 edge, 3 edges, but when we total these values up, we get a sum of 3. That means this path is actually shorter than the path up here. So it's not always clear, right? That's why we need an algorithm. And that's exactly what we have. We have Jigsaur's algorithm, and we're going to be doing a breadth first search, right? So starting at this node, the start node 1, we're only going to be possibly visiting nodes that are right next to our frontier, right? Depth first search would be we just go one direction and we just keep going, right? But breadth first search is we're going to do this layer by layer, right? We're going to go to the first layer, the next layer, and so on if we had a bigger graph, right? That's how breadth first search works. And every node that is on our frontier, right? So if this is our starting point, we have 2 options of nodes we can visit, this node or this node. These both are going to be added to our min heap, and we're only going to visit the one with a shorter path. That does make sense so far, doesn't it? It makes sense that we would want to visit this node because it has a shorter path rather than visiting this node first, which has a longer path, right? That makes sense so far. That's why we're using a minimum heap. Minimum heaps can get us the minimum value pretty efficiently, right? Every time we want to get a minimum value from the min heap, it's just a log n operation. Okay, so the way we initialize this algorithm is we know that we're starting here, right? What we're going to actually do is add this node to our min heap initially, right? So, and in our min heap, we're going to be keeping track of 2 values. Obviously, the path length, right? Because we're always going to be popping from the min heap based on the minimum path, right? So that's like our key value. That's what we actually care about, right? That's what's going to determine which one we pop. But we also want to keep track of which node it is, right? So initially, the path to reach the initial node 1 is 0, right? Because that's where we're starting. So it doesn't cost us anything to get there. And the node itself is obviously 1. So this is how we're going to start. Then we're going to pop this value. It's only one value so far, so it's simple of where we're popping, right? Once we pop this value, what's our next step? Well, like I said, this is a breadth first search, right? So we're going to take a look at the node over here. It's 1. We're going to look at all of its neighbors, right? It has 2 neighbors, right? We're checking that first layer. We're going layer by layer with breadth first search, right? So this is our first layer, right? We're going to take the first neighbor, 3. How long does it take to reach 3? 1. We're not visiting it yet. We're simply adding it to our min heap. So the path length is 1, and this is for node 3. The other node that we can reach is 2. The path length is 4. Let's add that as well. 4, and the node is 2. And since we've already visited the node 1, we can cross it out now. So now we're popping another value. This time we have 2 values, so which one are we going to pop? Well, this is a min heap, right? We're going to pop the value with the minimum path. It's this one, right? Of course, that's the one with the shortest path. That's what we're going to pop now. So as we pop every element, we're basically determining the minimum path. So now we can say for sure that the minimum path to reach 3 takes us 1, right? Because 1 was the value that we added to our min heap. And again, we're just doing a breadth first search. What are all of the nodes that 3 has neighbors with? It only has neighbors with 1 node, right? This 4, we have a directed edge going exactly to 4. So let's add 4 to our min heap. So we're adding the node 4, right? So that's what we're going to put in the node position. What are we going to put in the path position? Are we just going to put 1 because it only takes 1 for us to get there from 3? That's not actually what we're going to put. We're going to take the total that it took to reach 3, which was 1, and it's taking us another 1 to reach 4. So we're going to add the total to this, right? We're not just keeping track of the single one. We're keeping track of the total path it takes for each node. We want to know how long it takes to reach node 4 all the way from our starting position. We care about the starting position. So when I put the path value, the path length for this node, I'm going to put a 2 value. So now we are once again done with this node. So now again, we are going to decide which one are we going to pop from our min heap. We want to pop the value with a shorter path. So we're going to pop this one. So now we're at this node, right? And how many nodes can this node reach? Well, it only has a single outgoing edge to this node 2, right? And we see that 2 has actually already been added to our min heap, right? But the only difference is this time, and I'm running out of space, so I'm just going to add a little slot, is that for this 2, first of all, how long did it take to reach this? It took a distance of 2 to reach this 4. And plus 1 means that to reach this 2 now, it's actually a distance of 3, which is shorter than this one, right? So now we can actually add that same node 2 to our min heap, but this time we're going to have a distance of 3, which is shorter. So we visited this node, and now you can see that we only have 1 node remaining to visit. Good thing for us, both of our options in the min heap lead to that node. Which one are we going to pick? It's a min heap, so we're going to pick this one. 3 is less than 4, so we're going to pop this from our min heap. So now we finally popped the last node. It's a path length of 3. So now that we've reached every single node in our array, and by the way, this node does not have any outgoing edges, so we don't have to do anything more. And even though we do have a value left in our min heap, once we pop it, we're going to see that it's the same node that we've already visited. We visited this 2 node, and we visited every node now, and you can see the max value that we got in terms of length is 3. So 3 is going to be our output in this case. It takes 3 units of time or whatever for us to start at this position and then send a signal to every other node in the graph. So analyzing the time complexity of this problem is actually a little more difficult than you think. So I'm going to use E to tell us basically the number of total edges inside of our graph that we're given, and V for the total number of nodes or vertices that we're given. And just so you know, the maximum number of edges that we could possibly have is about proportional to the number of nodes squared, because like it's just kind of how it works. So like if we had 2 nodes, or rather 3 nodes, you know, we have bidirectional edges for every pair of nodes. And if you just basically, this is just something that's true, and that's what I'm going to assume. So the max size of our heap could actually be V squared, even though we have, let's say, 4 edges. We notice that some of the or rather, we have 4 nodes. We notice that some of the nodes could be added into the min heap multiple times. That's dependent on the total number of edges. That's why we're saying V squared is the total number of nodes that could be in the heap. So every heap operation is possibly worst case log V squared. And how many times are we going to be doing this operation? It's going to be E times worst case, basically the number of edges, because for every edge is how many times we can add values to the heap, right? So, and the way logs work, logarithms, if you take this 2, we can actually get rid of that 2, put it over here, right? Put the 2 over here, and we know how big O complexity works. We don't care about constant values. So this 2 actually goes away. So the overall big O time complexity with a priority queue for Jigsaur's algorithm is going to be E log V. This is just the general overview. Now let's get into the code. So we're actually given a list of edges, and we want to create an adjacency list of that first for Jigsawer's algorithm. So the first thing I'm going to do is create a dictionary or a hash map of edges. Initially, it's just going to be an empty list. So I'm going to go through every edge in the input. So for every edge u, I'm going to get a list of all of its neighbors, right? Because we know that that's pretty useful for Jigsawer's algorithm. We're going to basically get every single outgoing neighbor. So v is the neighbor node, and w is the weight of that node. So we're going to add that to edges list for u. So this is just creating an adjacency list for us, which is going to be useful. Now I'm going to create that min heap. We remember that because we know it's going to be 0. So two values. This is this node. It's already max of what it already is, and the max of the weight that we just got. The weight is, remember, the time it takes to reach this. The neighbor of 2 is min heap is just 1. Them is that to understand the min. We know we visited. Remember the one. It was pretty difficult. I the channel a lot.
Oh, my 5-minute break, guys. I forgot about it.
Nothing to worry about.
Hey everyone, welcome back, and let's write some more neat code today. Today, let's solve minimum cost climbing stairs. And this problem is very similar to another problem that we've solved that's called climbing stairs. And honestly, I think this is probably one of my best videos explaining dynamic programming. I really walk through all the steps from recursion to memorization to dynamic programming. So I will link this video somewhere on the screen or somewhere in the description if you want to take a look. It's very similar to the problem that we're solving right now, which is minimum cost climbing stairs. It's just a slight variation of that other problem. So we're given an integer array called cost, where cost of I is the ith step on the staircase. And if we pay that cost at index I, then we can either climb one step or two steps from index I. So in this example over here, we're given an array of 10, 15, and 20. What we're told is that if we pay this cost, if we're at this position, right, and we pay the cost of 10 from this position, we can either take one step, which will land us in this position, or we can take two steps, which will land us in this position, and we only have to pay a cost of 10 to do that. And also, we are told that we can actually either start at index 0 or start at index 1. So we can either start from this position or we can start from this position. And our goal is to reach the top floor of this staircase. So you're probably thinking, okay, let's just start at position index 0, right? Take a jump of 2, which costs 10, right? Because we're taking two steps starting from here. So that costs 10. Then we reach this spot, and then we're done, right? We've reached the top floor. So therefore, the answer is 10, right? Well, not quite, and it's kind of tricky. I think it's really their fault that they worded this problem kind of poorly. In this case, the answer is actually 15. Why is it 15? Well, it's pretty simple. It's because this is the last position in our cost array, but this is not the top floor. The position right after that is considered the top floor, which, yeah, they don't really specify that anywhere in the description, which is kind of dumb, but that's the thing. So the reason why the answer is 15 is because remember, we can either start at this index or we can start at this index. If we start here, then we can take a jump of 2, which will land us at the top of the staircase. It only costs us 15 to do that. Or we could start at 10, take a jump of 2, and then take a jump of 1, which would cost us 30. Or we could, from 10, jump to 15, and then take a double jump, which would cost us 25, 10 plus 15. So clearly, the minimum was when we start at 15 and then just take a jump of 2. So then the result is 15. So then your next idea might be, let's just be greedy, right? Why not always, let's start at one of the positions, either this one or this one, and then always take two steps, right? Why exactly would we ever want to take one step when we could take two steps, right? And it costs us the same amount. Well, there's an answer to that question, and let me show you an example, a counterexample of why sometimes we would want to take one step rather than two. The main reason is because maybe if we take two steps, there's a value over here, something like 1,000, right? A really big number, and then we have to either take one step or two steps, but either way, it would cost us 1,000 if we land here. Or we could take maybe one step, and yeah, we'd have to pay 15 and then have to pay 20, and then we could go take two steps to maybe a value over here that's really small, like 5, which would skip us a value like over here, which would be 1,000. So you can't really be greedy. And actually, the second example down here is another reason, is another counterexample of why we can't always take two steps. So let's really try to understand how we can at least brute force this problem, because we've noticed that from every spot we have two decisions, right? Take a jump of 1 or take a jump of 2, and we can't just be greedy and take a 2 jump every single time. So let's try every single possibility. And if you've watched any of my videos, you know that we like to do decision trees when we're brute forcing. So suppose we start here, we start at index 0, and we have 0, 1, 2 to this index, and this index is out of bounds, and that's when we know we've reached the goal and we can stop. So initially we start at 0, right? We can either jump to index 1 or index 2, and the cost if we jump to index 1 would be 10. The cost if we jump to index 2 would also be 10. Now, if from index 1 we can either jump once, right, meaning we jump to index 2, or we can do a double jump and jump to index 3. Of course, if we're at index 1, the cost to jump from there is going to be 15, whether we take a one jump or if we take a double jump. From index 2, we actually only have one choice. We can take a single jump, which will land us at index 3, which is actually out of bounds. If we take a double jump, we'll get to index 4, which doesn't really make any sense because that's also out of bounds. So in this case, the cost from jumping from index 2 is 20, so we can put that. Now, just so you know, once we reach index 3, which we already have done in 2 of our paths, as you can see, we can't really go any farther from here, right? So what we're going to say is, as we've stopped here, we want to know, okay, we reached the end, right? We want to know what was the minimum cost to reach this position. So one path, if we jump like this, the cost was 10 plus 15, which is 25, right? That's the total cost to reach this. Taking this path, it was 10 plus 20, which is larger. It took 30 to reach this spot. But we're not quite done yet. We know we can't go in this direction, so we're done here, but there's still one node in our decision tree that we can continue to traverse. So from index 2, we can take another single jump and then get to index 3, and of course that's going to cost 20 to do that, and so the cost is 20, so you can already tell that this is definitely not the solution. This took about, 45 to reach index 3, so definitely not good. You can see there were 3 different ways for us to reach the goal, and among all of these, the minimum was 25. But remember, if we go back to the actual description, the answer to this problem was actually 15, so why didn't we end up with the correct answer? And it's pretty simple, because remember, we were allowed to start at index 0 or allowed to start at index 1, but clearly in this decision tree, we started at index 0, so don't we have to draw another entire decision tree starting at index 1? Well, if you're clever and you take a look at this picture, starting from index 1, don't we already have that entire decision tree? Just look over here, right? We started at index 1 here. Now, we did do some work before we got to index 1, but can't we just pretend like that doesn't exist? Can't we just reuse this entire decision tree? Obviously, we have to modify the number.
I think an easier approach we could definitely do would be we can definitely do a hash map. Previous map. Okay. Yeah. For I, and index, index, and num, and you enumerate nums. We want to enumerate nums. We want diff. The difference is between the target we're trying to hit, subtracted by the value of num. If diff in previous to the map, meaning it's already in there, return pre-map of the diff and I. Else, if it's not, we have to add it to the pre-map. Index. Okay. And if it's already here, we just return false. We get out to here somehow. In. Oh, messed up, sorry. Awesome. We're given an array of strings for the longest strings that
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem longest common prefix. We're given a list of strings, and among all of these strings, we want to return whatever is the longest common prefix. Now, what is a prefix? Well, it's just a portion of the string. So for example, the string flight, a prefix is just any portion of the string starting from the beginning. So f is a prefix, fl is a prefix, fli is a prefix, flight itself, the string itself is a prefix. As long as it starts from the beginning and is continuous, then it's a prefix. And we want to return the longest common prefix among all of these strings. So, what's the intuitive way to tackle this problem? Well, look at the beginning, right? All three of these strings start with an f, right? So f is a common prefix among all of these strings. Let's look at the next character, l. L is the second character in all of the strings. So another prefix that's common among all the strings is FL. Now let's look at the third character. O is the third character in this string. O is the third character in this string. And I is the third character in this string. So unfortunately, FLO is not common to all three of the strings. It's common to these two, but it's not common to this one. So FL is going to be the longest common prefix that we have, so that's what we can return. So the problem really is that simple, but there are a couple edge cases that can trip you up if you are a beginner. So we're going to be focusing on that, especially when we code it up. So basically, we are going to simultaneously iterate through all of the strings that we're given. One of the strings could be shorter than the other string. So for example, if we weren't even looking at this string, we can see that these two strings, this string and this string, they both start with flow, right? So flow is a common prefix to both of these two strings. Then if we got to the fifth character, we'd see that, okay, E is the fifth character here. This string does not even have a fifth character, right? So if we get out of bounds out of one of the strings, then we know we can stop, right? And that makes sense, right? Flow would be the longest common prefix among these two strings. So what's going to be the time complexity of this solution? Well, potentially we're going to have to go through every single character of every single string. That would basically be the case if, we had, let's say we had flower and we had it multiple times, right? Then we'd have to potentially iterate through each of those flower strings, right? Because they're common, so we wouldn't stop. And then we have to go through every single character. So the overall time complexity, let's say, is going to be n, where n is the total number of characters that we're given. Or if you want to say that n is the average size of the string, and we have m different strings, then you could say this is the time complexity, right? However you want to formulate it. But overall, we're going to just have to iterate through each character in the entire input once. With that said, we're ready to code it up. So the first thing we're going to do is initialize our result. Remember, if let's say we didn't even have a common prefix among any of the strings, right? They all started with a different character. Like we had A, we had B, we had C, right? There's no common prefix among these three characters, so then we just return an empty string because there is no common prefix. So we initialize our result. Then we want to simultaneously iterate through all of the strings, right? So we're going to use a pointer I to indicate what index that we're at in the strings, and we're going to go through, let's say, through every single character of, let's say, the first string, right? I'm just putting the first string here, strings at index 0. This is just the first string. I'm using that arbitrarily, right? Because it could be possible that this string is not the shortest string in the input, right? In which case we want to stop this for loop earlier than it's actually shown right now. So we'll have to remember to handle that case. I'll handle it slightly differently than using a conditional out here. So, okay, so we're iterating through every index. We want to now iterate through every single string and make sure all the strings have the exact same character at index I. So let's go through every single string. So for S in the list of strings that we're given, we want to check that every single string at index I is the same. So let's compare this arbitrary string S to the first character of the first string, right? We could pick any of them, but we just want to make sure that they're all the same. So we'll just make sure to choose the same one every time. So we'll go to the first string, right? Strings at index 0 is the first string in the input, and then we'll go to index I of that string. So as long as they're equal, we're going to continue. If they're not equal, though, which is this case, then we're going to have to return, right? We're going to have to return whatever
our result is so far, because we know that whatever this prefix is, that's going to be the result, because we can't make the longest common prefix any longer. But there's one case that we didn't think about. What if we went out of bounds, right? What if the string s is out of bounds? Because we know this is going to be in bounds because that's our I pointer up above, right? I is always going to be in bounds of the first string because that's what we're iterating through up over here. But this string might go out of bounds. So before we check this condition, we're going to make sure that I is in bounds. So we're going to say that if I is equal to length of s, which means it's out of bounds, right? Then we're going to also return, right? We're not even going to check this line of code. If this evaluates to true, we'll immediately return. That's how Python works with the conditionals. If the first one is true, we don't even check the second one. And so that is the entire logic of the for loop. But remember, every time we go through a character, we want to add it to our result. So we can do that pretty easily like this. We can go ahead and add that character that is common among all the strings to our result. And then once we're done with all of that, we can go ahead and return the output result, and we'll be good to go. So I'll run it to make sure that it works. And as you can see up above, yes, it works, and it is pretty efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider pretty easily like this.
So we have a prefix for just the first strings and 0. For in range 1 and the length of strings, j is equal to 0, while j is less than the min len of prefix length of strings I boop boop if prefix j does not equal string s of I and j, we could break out of it, and then j plus equals 1. And prefix is literally just going to be the prefix, however long j is. We can just return prefix. Cool. Do this once. I like that. Give an array string we can maybe sort every letter.
Hey everyone, welcome back, and let's write some more neat code today. So today let's look at a good question to practice the fundamentals, group anagrams. So we're given just a list of strings, and we want to group all anagrams together. So for example, we have tan and we have nat, and they are anagrams together. So in the output, we're going to group them together into one sublist. And how do we know these two are anagrams of each other? The first one is tan, the second one is nat, and you see if we swap the n and the t, then we get tan, right? And that's the same as this. So by rearranging the characters, we can get equivalent strings, so these two are equal. So another way of looking at it is two strings are anagrams of each other if we take each of them and sort them, right? So if we sort both of these, we're going to get ant, right? For both of them, because that's the sorted version. So if they're anagrams of each other, when they are sorted, they should be equal, right? So one way to group anagrams together would be to take each one of these strings in the input and then sort them. But the time complexity of that is going to be n log n, where let's just say n is the average length of each of the input strings. So that's how much it takes to sort each of the strings, and we have to do that m times, where let's say m is the length of how many, like basically how many input strings were given in the first place. So you can see that this is going to be the overall time complexity. So my question is, can we do better than this? And actually the simple solution in this case happens to be more efficient, and let me show you that solution right now. So one also condition that we're given is that each character is going to be from lowercase a to lowercase z. So at most we have 26 unique characters, right? So let's just have an array called count. So for each one of these strings, we want to count the characters from a to z, right? How many does it have of each? So we know it has one e, one a, and it has one t. And for this one, we would see that the exact same thing is true. It has one e, one a, and one t. So if we use a data structure called a hash map in this case, and in this case our key is going to be this over here. So this is what we can use to identify anagrams, and then our value is going to be the list of anagrams. So in this case, how many strings or which strings have this pattern of count 1e, 1a, and 1t? Well, we see there's one eat, there's one t, and there's one last one
8. So those are going to be the values. We'll have a list of them, E, T, and then 8, right? So we'll have 3 strings, and as you can see in the output, it's a little messy, but that's what we have here, right? So these 3 are grouped together, so we're going to use a hash map to group them together. Since we're using a hash map, and all we're doing is counting the characters of each, and we know that we have a limit of 26 lowercase characters, the overall time complexity is going to be big O of M, where M is the total number of input strings that we're given, times N, where N is the average length of a string, because we have to count how many of each character it has, so we're going to have to go through every single character in a string. And since we are using count, right, or this array in our hash map, we're using it as a key in our hash map, we kind of also have to multiply this by 26, because that's what's going to be the length of our count array, but you know that this reduces anyway, so the actual time complexity is big O M times N. So now let's code it up. As you can see, though, this is basically one of those problems that can be solved with a hash map very efficiently. So let's create our hash map. We'll call it result. And so remember, what we're doing is we're mapping the character count of each string, and we're mapping that to the list of anagrams. So to do that, we of course have to go through every string that we're given in the input, and we want to count how many of each character it has. So we'll have initially a array. So we're gonna have 0 in it. We're gonna have 26 zeros, right? Because 1 for each character. So from lowercase a all the way to lowercase z. And now we want to go through every single character in each string, and we want to count how many of each character. So we want to map, in this case, a to index 0, and we want to map z to index 25. So how can we do that? Well, we can, one way at least, is just take the ASCII value of the current character we're at, C, and then subtract the ASCII value of lowercase character a. So as you can see, lowercase a minus lowercase a is going to be 0. Z, lowercase z minus lowercase a is going to be 25. So we do have it correctly because, for example, let's just say a is ASCII value 80, and I don't know if this is actually correct, but it's just a random value. Then b is going to be ASCII value 81, and so on. But if we want to map this to 0, we know one way to do that is take 80 minus 80. If we want to map lowercase b to 1, we can take 81 minus 80, right? So that's basically what I'm doing here in case you haven't seen something like this before. And so we're just going to increment this by 1. We're just counting how many of each character we have. And now in our result, we want to add, so for this particular count, we want to append, we're going to append this string s. So we want to group all anagrams with this particular count together. Now, what if this count does not exist yet? Well, I'm actually going to change this dictionary to a default dictionary or a default hash map where the default value is a list, so we don't have to deal with one edge case. And also, right now our count is a list, but we know in Python lists cannot be keys, so we're actually just going to change this to a tuple because tuples are non-mutable. But mainly this is Python stuff. You might not have to worry about this in other languages. And so that's actually it. So now in our dictionary, we have grouped the anagrams together, so we just can take result.values. We don't want the keys anymore. We just want to return the values, the anagrams grouped together, so we can return that, and we're actually finished. So this is the optimal m times n solution, where m is the number of strings we're given, and n is the average length of each string, how many characters are in each string. So I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Result is equal to default dict, which is going to be list for s in strings. Count is going to equal the index times 26. Online Python IDE.
everyone, welcome back, and let's write some more neat code today. So today let's solve the problem remove element. We're given an integer array of nums and a particular value, a second parameter value, and we want to remove all occurrences of this value that we're given as the second parameter. We want to remove all occurrences of it from the other parameter, the nums array, and the trick here is that we want to do it in place, meaning we want to do it without allocating another array. We want to do it just with the input array that we're given. So basically, if you read the next paragraph, since we want to do it in place, the main way that they want us to actually implement this is by taking all the values in the input array nums that are not the particular value, and then place all of those at the beginning of nums. So suppose we had k values in the array nums that are not the value, the special value that we want to remove, then we would return k saying that, okay, there's k values in nums that are not that special value, and all of those k values have been placed at the beginning of the array in place. That might seem kind of complicated, so it's best understood with an example. So take a look at this input array that they are giving us, and the special value that we want to remove is value 2. So we want to remove all occurrences of 2. 1 does not actually matter, right? Values that are not 2 at the beginning of the trick to do values are not 2. But doing the actual in-place modification is tricky if you're a beginner, so let me explain it. So how would we want to do this? Of course, we can see the first two values. These are not 2, so we don't have to do anything with them, right? Okay, the next values are 2, but we can't just delete them, right? We have to replace them with other values that come after them, right? Basically collapsing these values onto the 2s that we want to remove. So we read the 2s, then let's say we get to a 3, right? Where do we want to put this 3, right? We don't know that there's anything else in the array. There could be, there might not be. Where would we want to put this 3? We could put it in this spot, replacing this 2, but it would be much better to put it over here, right? Replacing this 2, because we want to put all the values that are not 2 at the beginning of the array. So it's better to put it here. So suppose we do that. We replace this with a 3, and the real 3 can just stay here for all we care. And then next, we're going to get to a 0. So this is also not a 2, and we want to put this over here, right? We know there's another 2 over here, so let's put the 0 over here, right? So basically what we're learning by just going through this example is it might be very helpful for us to keep a pointer, let's call it k, or let's call it I, or whatever you want to call it, a special pointer basically telling us next time we find a non-2 value like 3, 0, 4, where should we put it, right? We should put it replacing the 2, wherever the first 2 happens to be. And then once we do that replacement, right, we'll take our I pointer and then shift it by 1, saying, okay, next time we see a non-zero value, like 0 in this case, then put it over here. And then again, we take our I and then shift it. But this time, see, our I pointer is at a 3 value. But it's okay for us to, next time we get a 4, to put the 4 over here, replacing the 3. That's perfectly fine, because remember, we already took this 3 and then put it over here. We already shifted it by once. Okay, so that seems pretty simple, what we need to do when we see a non-2 character. But what happens when we do see a 2 character, right? Let's say our I pointer is over here, and then we arrive at this 2. Would we want to put the 2 over here? No, because we only want to put non-2 characters at the beginning of the array, right? We don't care about the actual 2 character. And I've been using I for this, but it's probably better to use k. This k value will actually be the output value that we end up returning in this problem, because this k is going to be incremented every time we see a non-2 value. So it'll tell us by the time we've reached the end of the array, it'll tell us how many values are in the array that are not 2. So that definitely makes sense for us. Now, one thing you might be wondering is, we initialize our k pointer over here, but isn't the k pointer initially going to be at the beginning of the array? And suppose we didn't even have any 2s at all. What are we going to do in this case, right? We're going to say, okay, we have a 0. This is not a 2. So does that mean 0 is going to be swapped with itself? That doesn't really make sense. And then would we want to still shift our k by 1 because we didn't see a 2 in this position? And you're right, it doesn't really make a lot of sense to do it, but it elegantly does work out with the code, right? For example, if we did not have any 2 characters, right? Suppose these didn't exist and this didn't exist. How would the algorithm that I'm explaining, how would it actually run? Well, we'd see a k. We'd start with a k here. We'd say, okay, this is not a 2, swap it with itself. Okay, then k gets incremented by 1. This is not a 2, swap it with itself. Okay, k gets incremented by 1 to over here. Swap it with itself. Swap this with itself. Swap this with itself, and then we're done. And then by the end of it, our k pointer would be over here. It would be at position 5, and we would want to return 5 because that's the number of non-2 values in the array. And then this is what our array would look like. We didn't actually modify the array at all if this was the input array itself. So you can see that this algorithm, it's simple, but it does work in all the edge cases that we need it to work in. So it makes sense. And without further ado, we can now jump into the code. Okay, so now writing the code. Remember, the main thing that we're just going to be maintaining in this problem is just the k pointer. Initially, it's going to be at index 0, and then we are going to just be iterating through every single value in the input array. We're going to be doing that with a pointer I. So let's just get the length of the input array nums and then do that. Remember, if we see a 2 value, then we're just going to ignore it, right? We're not going to execute anything. But if we see a value that's not 2, or I keep saying 2, but we actually want the second parameter that was given to us called val. So if this is not equal to that special value, that's when we're going to be performing the swap. If we do see that special value, then we can just ignore it, right? We don't want to take that special value and then push it to the beginning of nums. We don't want to do that. And basically, from what I'm writing, you might actually recognize that this algorithm that we're doing is kind of similar to the partition of like a quick sort or quick select. By partition, in this case, we're taking all values in nums that are not this particular value and then putting them at the beginning of nums. That's what we're doing when we say partition. If that makes it easier to understand for you. But like I said, so if it's not the special value, then we can take this and then put it at our index k, which tells us where to put the next value. So we'll put nums of I at position k, and then we will increment our pointer by 1. This should be an I, not a k. So then we'd increment by 1, and then if it is that special value, then we won't do anything. We'll just skip it. And then once we're done with this, remember what we actually want to return is k itself. We don't want to return nums. We want to return k. So that's the entire code. Let's run it to make sure that it works. And as you can see on the left, it does work. It's pretty efficient. It says 12%, but I'm pretty sure this is as efficient as you can get for this problem. Feel free to correct me if I'm wrong, but I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.
Cool. Let's see the food's ready real quick, guys.
You. That's not what happened back there. You idiots just happened to be my best escape route. You're welcome. I had to get out of there so All Might could destroy that guy. I'll be like.
Okay. Sure. I have a tracker for every number. Probably something faster, maybe. Yeah, that's what I thought. Count is equal to default dict int. Result is equal to max count. We have them both equal to 0. For we can do for single num in nums count num plus equals 1 if max count is greater than count num. Result equals num. Max count is equal to count nums. This now allows me to keep return result. That's smart. There we go. What? There we go. We got it, gang. We got it. We've all done that. Let's keep going. Let's keep going down the list. We're at 8. Design hash set. Ooh. Design a hash set without using any built-in hash table libraries. Implement hash. Add. Insert value key into hash set. Bool contains key.
Hey everyone, welcome back, and let's write some more neat code today. So today, let's solve the problem, design hash set. And of course, we have to do it without any built-in libraries. This is pretty similar to Leetcode 706, where we designed a hash map. I've solved that question before, and this one is slightly more simple. And we really are only implementing the most basic features of a hash set, adding a key, removing a key, and checking if it contains a key. Now, of course, I'm sure you recall the hash sets cannot contain any duplicate values. That's not super hard to work around. Really, the hardest part about implementing hash sets or hash maps is, one, implementing the rehashing, because just like dynamic arrays, hash maps and hash sets can grow in size, and we don't necessarily want to start out the hash set with like a million spots available to us. But in the case of this problem, they tell us that I think we're only performing something like 10,000 insertions. So
that's pretty much going to be the max size of our hash set, and that's not super large, so we can implement that. That's probably why this is an easy problem. I think implementing like a real hash set would be definitely a medium. And the second part about implementing this is how do we handle collisions? And I'm going to pretty much be handling them in the most simple way, because I think that's usually sufficient for coding interviews, and that's using a technique called chaining, aka using a linked list. So now let's get into it. What's going to be the idea? Well, we're going to use an array because it's not like we can just invent new data structures. Usually we have to use like nodes or arrays to implement more advanced data structures. In this case, we're going to be using both. So our array, of course, can have an index, but the value of our array is going to be, in this case, a linked list node. And the reason we're doing that is because that's how we're going to handle collisions. And you'll see what I mean in just a second. Suppose the size goes from index 0 all the way up until 9999, because that's 10,000. And let's say we're just inserting a key, because in the case of a hash set, all we do is care about the keys. We don't have a key value mapping. When we're given a key, and in this case, we're only given integers, which further simplifies this problem, we need to map that key to some index in our array. And the easiest way to do that is using the mod operator. We're going to take that key value, mod it by the size of our hash map, which again, in this case, is 10,000. And when I say size of hash map, I meant the size of this array. So when you do that, we will never get a value that's larger than 9999. It'll either be from 0 up until this number. So it will be in bounds. That's guaranteed. Even if we're given a number that's larger than 10,000, let's say we're given 10,001 and we mod that by 10,000, well, we're going to get a value of 1. So it'll map somewhere over here. Let's do that. So that key value here is going to map to this position. So we're going to create a linked list node in this position. Why are we doing that? Well, you'll see in just a second. I'm not going to fill in the value just yet. But now, suppose we're inserting a new key value. Now we're inserting the key value 1. And when we mod that by 10,000, notice how it goes in the same spot. It also maps to the 1 index. So we have a collision. How are we going to handle that? Well, there are many ways to do it. Another common way is open addressing. I talk about that in my course if you're interested in that. And I also go into like details of how you can implement rehashing. But in our case, we're going to be doing it the more simple way. And that's by basically taking another linked list node and adding it to the end of this linked list. So this is really going to be a linked list connecting a bunch of nodes. And we can have multiple nodes here. Now, how do we distinguish between the fact that we also inserted a 1 and the fact that we also inserted 10,001? Well, pretty much just like I drew it. On the linked list node, each node is going to have a key, and the key is going to be the same key that we inserted. The reason this is important is because, as you know, we don't want duplicates. So if now I try to add 1 again, it's going to hash to this position. And by the way, when we take that key value and mod it by the size of the array, that is basically our hashing function. It's a very simple one, but I'm sure you can imagine that there are more complicated ones that we can do. And in this position, we're going to then look at the linked list. We're going to try to add another linked list node with a 1 value, but why would we add 2 of them? We know hash sets can't contain duplicates, so there's no need to add the second one. As soon as we see that we've already inserted one here, we do not need to add it again. And of course, we will implement contains the same way. That's very important in a hash map. We want to know, does the value 1 exist? And we would find in our linked list, yes, it does. But if we ask another question, does 20,001 exist? It would map to the same index, but in our linked list here, we would see it does not exist. And same thing when we're talking about removing keys from our hash set. We're going to go to the index that the key maps to, and then find the linked list node. If it exists, we're going to remove it. The way we're probably going to remove it is by taking the previous pointer and updating it so that it points at the next pointer over here, which pretty much deletes this node. So you can see why this is a pretty straightforward way of implementing a hash set. What about the time complexity and the space complexity? Well, in theory, in average case, usually if the length of the array is a prime number, it helps to minimize collisions. And if we implement rehashing, where we dynamically increase the size of the array as it gets really filled up, like we wouldn't want to have too many collisions in a single spot. And as we add more and more values and keys to the hash set, we're going to have more and more collisions. So at some point, we're going to increase the size of the array. But of course, we're not implementing that. If we did implement it all correctly, we can be pretty close to constant time in the average case, not in the worst case, but usually in the average case, every operation in a hash set is pretty efficient. And in most cases, people will just assume even the worst case time complexity is constant, like for most interviews. In terms of memory complexity, of course, it's going to be big O of n, where n is the number of keys that we have in our hash set. Technically, it's actually higher than that because we are pre-allocating the entire array. But I guess we could get technical and argue about whether this is constant size or big O of n, or maybe even bigger than that. But that's pretty much what I wanted to discuss. So now we can jump into the code. So you can see this is the definition that we're given. We need to implement these 3. The first thing I'm going to do is implement our constructor, where we're just going to pre-allocate the memory, which is going to be an array in this case. And I want it to be of size 10 to the power of 4, because that's how many calls are going to be made to add. So that's going to be the maximum number of keys that we're probably going to end up inserting. Technically, we could make it even smaller than this if we wanted to, but that would end up giving us more collisions potentially. So this is a pretty decent size to have it at. Instead of just initializing it to 0, I'm actually going to create a dummy node for every position in the array, because that will make handling the edge cases a tiny bit easier. But believe it or not, this is a bug. A lot of people make this mistake. When you multiply an array like this, it'll basically copy this exact same value in every position. It's not going to create a new list node for every position. It's going to copy the same one. That's a bug. And to fix it, basically, we say this for I in range 10,000. So this will create a new list node for every position. And in this case, this is a dummy node. We're not going to use it, but it's just going to help us handle the edge cases a little bit better. So first thing I should probably do is define that class up above over here. And it's going to be very simple. It's going to have a constructor that just takes in the key value, and it sets 2 fields. One, the key, of course, and second, the next pointer. And that should be sufficient. Now let's go ahead and implement the add function. And you're going to see it's going to be pretty similar to the next 2 as well. So the first thing we want to do, given a key value, is to hash it. And I could define a separate hash function down here, but since our hash function is so simple, I'm not going to do that because I want to save space and show you the entire code on like one screen. But I don't think it's a bad practice to have a separate hash function because that would make this design a little bit more extensible. So given the key, we want to mod that by the length of our hash set, and that will give us the index that this key is going to map to. And then with that index, what we want to do is get the head of the linked list, or what I'm going to call it is the current pointer. So then we can get it by saying set at this index gives us the head. And then we want to basically iterate to the end of that linked list to insert a new node with this key. So we can go ahead and do that. So while cur.next is non-null, because we want to skip the current node because we know it's a dummy node. So we're always going to be referencing the next node. And on each iteration, we're going to say current is equal to current.next, continuing to shift until we get to the end of the linked list. So this will stop when current is at the last node. So at the last node, we're going to say current.next is equal to a new list node with the specified key value here. And then we can return, and we don't really need to return anything, so I won't. But there's a slight bug. What about duplicate values? Well, if we detect a duplicate, we should probably just return immediately. We don't need to execute this part of the code. So here, before we shift our pointer, we can check if current.next.key is equal to the given key as a parameter. At that point, we just want to return. We don't need to do anything anymore. We detected the duplicate, so we can stop. And the reason I'm saying current.next key instead of just the current key is because, again, we want to skip the dummy node. So that's pretty much the add function. Now I'm going to clean it up a tiny bit. You can see that this index is always going to be used right here. So I'm pretty much just going to cut that and move it down here just to save a little bit of space, because pretty much we're going to be copy and pasting this entire thing for the remove function and the contains function and just modifying a couple lines of code. At this point, I'm just going to turn my brain off because I've done so many algorithm problems and just say, okay, we're going to start at the current node. This time we want to remove the node, so we don't need to do any type of insertion over here. And we only want to remove the node if it exists. So what we're going to be doing is pretty much here looking for that key, except instead of returning here, before we do that, we probably want to just remove it. And like I said, we're going to do that just by shifting the next pointer
to the pointer after that. So we're going to say current.next is equal to current.next.next, just like I kind of showed in the drawing explanation. Otherwise, we just want to continue through with the linked list. And once again, I'm going to copy this into the next function. And this time we're looking for this key. So if we do find the key, instead of removing it, we probably just want to return true, because we do need to return a Boolean this time. So let's return true if we find it. Otherwise, if we get to the end of this, then we can just return false. So not a lot of changes there. If you can implement one of these functions, you can pretty much implement the other two. And it just barely fits on one screen, so that's good. Now let's run the code to make sure that it works. And of course, there's a bug, and it's not even with our hash set class. It's with the list node class. We probably want to set the next pointer not to next because it's not even defined yet. We can probably just set it to null initially. Now let's run it to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If you found this helpful, please like and subscribe. If you want to see a more detailed implementation, you can check out leetcode.io. Thanks for watching, and I'll see you soon.
Cool. Yo, Chilzers, what's good? Your boy has been thugging it out. I am a different man. I am now a different man. I have been grinding Leetcode. I am now at hour 12. I am a different man now, Chilzers. I am a different man. No one knows. Oh, I'm not learning binary. I'm not setting up a binary search tree for that. That's insane. What you been up to, bro? What have you been up to? So we got... If I get this problem, we can do a brute force way. Dude. You don't want to know, Chilzers. You don't want to know. I've so far finished a total of how many problems now? 42. We're going to be going until I get all 250 done. Or as close to. Yeah, I'm a different man now. Working and planning my move to Chicago in a few months. Oh, dope. Did you get a new role? That's exciting. Self.data. If key not in self data dot append key. Now my fiance did, so we packing up that move. That's why work from home is so nice. Yeah, I agree. It's awesome, Childers. Make sure y'all celebrate. Y'all better be celebrating. Nice little get together, little surprise party. Oh my. Just a simple list. The brute force way. Good to know. Now if we take the approach. Ugh. Oh my. What do you mean Boolean? Oh my. You still been playing League? This is a Boolean approach. False. You already know we have a bucket list for our current city, so me and her have been blasting through dates and stuff. That's exciting. That's exciting. Dude, I hope you guys, when you guys get married, have a fun marriage. 2, 3, 4, 5. Oh, my eyes. 10,000. Oh my. I am a different man. This is the Boolean approach. Wow. Self.data. How does this work? You're welcome. Listen, Childers, when you become big and famous, I aspire to be like you. Someone great. But me, I gotta get through this. The interview's coming. My chance at Google is coming. I gotta get this through. And guys, your brother is jobless. I am going back to class starting Monday, so we got bad news for me too. So no more morning. No more morning. Wait. I forgot what's my schedule on Monday. I didn't even check. Holy crap. Dude, I didn't even check my schedule for Monday. Oh my. Ah, we're chilling. Never mind. I thought we would be worried for a second. 3 to 4. Wait, what time is my interviews? Oh, yes. Let me check real quick. Guys, I am letting you know right now. I hope nobody has to leak code ever again. This is the worst ever. I've done so many coding problems. I want to throw up. You guys don't understand. But you know what's crazy? It feels like right now this is me after like 20 games of League. That's how bad it's been. Let me check it out. Can't show you guys the email. Y'all see, y'all been seeing too many bad things about me. 4 to 4:45. He'll forgive me. My professor will forgive me. Don't worry. It's okay. I am not rescheduling. I want to be rich and famous. Rich being famous ain't for me. When you get famous, though, let me know how it is. Childers, when I'm famous and I'm running around on the streets having my clothes ripped off because I'm so famous, I'm gonna be like, yeah, this is what I wanted. This is the life I wanted. You can hear the slight like regret, but deep down I'm like, this is the choice I made. Oh, dude. Dude, I have the worst schedule. Holy crap, guys. Guys, since they took back my offer, mind you, children, I forgot to give you some background information. I did a video where I trolled a U.S. senator, and then my job found out, and they weren't happy with it. That's your burden to carry. I'm all yours, yeah. So I did a video where I trolled a U.S. senator, and then I had a job offer lined up, and they found out about the video. And they saw the video and they were pretty upset by it. So now I am jobless and I've been trying to find a job, but I have until Friday to find a job, and I have received a bunch of offers. But the thing is, guys, I'm the type of guy to go above and beyond. Okay, I'm not the type of guy to be like, oh, I want to be some willy-nilly software. No. I'm the type of guy who goes to go balls to the wall. You know, I'm the guy who's the face. You know what I mean? I'm not happy with anything I got. So, I might be going back to college, but it's completely okay. Because listen, brothers and sisters, your boy might be alright. I just gotta keep going. Oof. I just gotta keep going. Oh my, dude. All tickets belong to someone who originally departed from JFK. Your objective is to reconstruct the flight path that this person took, assuming each ticket was used exactly once. There are multiple valid flight paths. Return the less illogical graphically smallest one. For example, itinerary JFK-C. May you assume all tickets should inform at least one valid. Buff to Houston. Houston to C. And JFK to Buff. Buffalo to Houston and Houston to C. A, B, C, D, E, F, G. Okay. Maybe we add all the flights, the JFK letters together. It's good sort of draw like that. Find every unique path. I don't know how we should store it. Fuck it. I have no idea. Oh, it's a Google question.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem reconstruct itinerary. This is a pretty difficult problem, but it's doable if you have a good understanding of graphs and graph traversals, especially DFS, which we're going to be using in this problem. But we're given a list of airline tickets, and these tickets are basically a graph edge. We have a from and a to, so basically a source and a destination, and it connects two nodes together. In this case, the nodes are going to represent airports or cities. And basically using this list of tickets, we want to reconstruct the itinerary, and basically what that means is we want to reconstruct the flight history of a person who had this list of tickets. All of the tickets belong to someone who departed from JFK, so no matter what, this is going to be our starting edge in our graph. So basically if you take a look at this picture, we're always going to be starting at JFK, so we're pretty much guaranteed that JFK is going to be a node in our graph. They also tell us that we can assume all tickets form at least one valid itinerary, so basically we're guaranteed that there is a solution, and in the solution that we create, we have to use every single ticket exactly once. And there's one last thing that they tell us. There could be multiple solutions, and if there are multiple solutions, we want to return the one that has a smaller lexical order, basically the one that comes first in sorted order. And you can't really tell that from this example because there's really only one solution, but let's take a look at another. So here we have a different graph. Let's say, A was JFK in this context. I'm just using ABC to keep it simple, but we're starting at A. We could, we want to go over every single edge, basically. Each edge represents a ticket. We want to go over every single edge, and we want the history of the destinations to be our result. So, let's say we're creating our result. A is going to be first, and then, what we
could do is we could say, okay, let's visit C first, right? We get to C, and then we go back to A, right, from C. So what we could say is, okay, we first go to A, then go to C, then go back to A, and then we go to B, and then we go back to A from B, and then that would leave our result looking something like this. That's one possible solution. But the other solution would have been to go to B first and then go to C. What that would have looked like is A, B, A, C, A. Now, which one of these has a smaller lexical order? Which one of these comes first in sorted order? Well, the first character A is the same, but the second character could be B or C. Which one of these comes first? B comes first. So, of course, of these two, we would prefer the second one. We would return the second order as our result. So that's something to keep in mind. And the way we can actually handle this is going to be pretty easy. I'll show you how we can make sure that we return the smaller lexical order result. Now, this example is very simple because there's really only one ordering that we could possibly create. And to get that ordering, what we could do is just run DFS starting at JFK. We know we're always going to start at JFK. We create a DFS running on this. And using this DFS, technically, we are allowed to visit the same node multiple times, as I showed in the example just a moment ago. But what we can't do is go over the same edge multiple times. We can't reuse one of our tickets. But in this case, if we run a DFS starting at JFK, what we'll get is JFK first, then this one, then this one, then this one, and then this one. So there's really only one ordering, and you can see that that's the output for this example, the expected output. And so that's what we can return. But if we, of course, had multiple choices like this, or adding a bunch more edges, and we still have to go over every single edge, and we have to return the smallest flexible order, let's see how we can do that algorithm. So like I mentioned, you really have to have a good understanding of graphs to be able to solve this problem. I'm going to assume you kind of already know DFS and the basics of graphs. So what we're going to use to do the traversal on this graph in the first place is create an adjacency list. Of course, we're already given the list of edges, but we have to actually create an adjacency list out of that to be able to traverse over the graph. And the way we're going to be creating this adjacency list is just going to be by using a hash map. We're going to map every single node to the every single source rather to the possible destinations that we can take. And the easiest way to build an adjacency list is just kind of iterate over the input, which is tickets in this case, right? It's a list of source destination pairs. So what we would do is say, okay, JFK has San Francisco SFO. At least I assume that's San Francisco. And then it also has a second one, Atlanta ATL, and we can start adding those to our adjacency list. Like this is the list, this is the source, right? So from JFK we can travel to these two cities. But what I'm going to tell you right now is that we should have this list in sorted order because we're going to be running DFS, and as we run DFS, we're going to start at the first possible source that we could visit from JFK, right? We're going to try SFO, and maybe we find a result starting at SFO. In that case, we could return that as the result. But what if it turned out that maybe we could have also found a result, going to Atlanta first rather than SFO? In that case, this is the result that we would prefer because it comes first in sorted order. So what we want is for each of these lists to be in sorted order, and we could build the adjacency list and then sort each of these lists independently. But the easier way to do it is actually just to sort the input, and I'll show you why. Because the way we're going to be sorting the input is by doing this. These are pairs of values, right? The first value is going to be the first key that we're going to use to sort. So these two JFKs would be next to each other. But then if there's a tie between the first value, then we want to use the second value as our sorting keys. So among these two, which is going to come first, SFO or ATL? Of course, ATL because it comes first. That's just something to keep in mind. So if we have this in sorted order, then our adjacency list will be sorted by default, right? And I'm actually going to build this adjacency list now, assuming that this thing is in sorted order, or at least I'm going to be going through the sorted order version of this list of tickets. So first is going to be ATL, and it has JFK as one of its destinations. So let's do that. And ATL also has SFO as one of its destinations. So let's add that. Next we have JFK. It has Atlanta as one of its destinations, and it also has SFO as one of its destinations. And then lastly we have SFO, which only has one destination, which is ATL. So let's add that. So now we're going to start running our DFS. So let's focus on the picture now. So we're going to be starting at JFK. We have two outgoing edges from JFK. We could go to SFO or we could go to ATL. Which one are we going to decide? Well, we're going to look at our adjacency list and see which one comes first. Well, ATL comes first, so let's visit ATL. So we're going to go along this edge, and now we're going to be at ATL. And when we do that, we're actually going to remove ATL from our adjacency list, at least temporarily for now. And by the way, as we go along this, we're also going to be building our result. Our result is just going to be the travel history of these airports. We know initially we started at JFK, and right now we just visited ATL, so that's going to come next. Okay, now from ATL, we have two outgoing edges. We could go to SFO or we could go to JFK. Which one are we going to decide? Well, let's see which one comes first in sorted order. It's JFK. So let's go to JFK next. So we're going back to JFK. So we visited both of these two edges, and let's remove JFK as a destination from Atlanta. And in our result, now let's add JFK again because we started at JFK, then we went to Atlanta, then we're back at JFK. Now from JFK, we only have one outgoing edge remaining, SFO, and that you can tell from our adjacency list as well. So let's pop SFO. Now we're at SFO. Let's add that to our result as well. Now from SFO, we only have one destination. It makes things easy for us. That's Atlanta. So let's pop Atlanta from here. Let's go along that edge, and let's add ATL to our result. And from ATL, now we only have a single edge outgoing. It's to SFO. So let's pop SFO, travel along that edge, and add SFO to our result. So this was a valid way because we just visited every single edge. How exactly do we know we visited every single edge though? Well, our result is going to be keeping track of all of the nodes that we visited in our graph, right? Not the edges. We know every time we visit one of the edges, we're going to be adding another node to our results, and we know that we actually initially start with a single node, which is JFK, before we even travel along any edges, right? We start at JFK. So basically, we know we are finished when the length of our results array is equal, so I'll write it out, is equal to the length of our tickets plus 1. So down here you can see when length of result is equal to length of tickets plus 1, that's how we know that we are done. The plus 1 comes from the fact that we already start with a single node in our result array, and then every other node comes from traveling along one of the edges in our graph. So that's the main idea. Now in this example, it was kind of simple for us because the first solution ended up working, the first path that we tried ended up working, but if it didn't, suppose we actually had a graph that looked like this one, and let's say we started at the A node. In this case, we have two choices of where we could go. We could go to C first, or we could go to B first. We're going to choose B because it comes first in lexical order compared to C, so we travel along this edge, and we end up visiting the B. Okay, well now we're stuck here. There's no outgoing edges from B. We can't even get back to A. So what we found is we tried to be greedy. We tried to take the first character that came, right, the alphabetical character, but it didn't work out for us. So we end up backtracking. We say, okay, we're actually not going to travel along this edge, at least just yet. We're actually going to travel to the C first, even though it comes after in order compared to the B, just because we know that at least here we might be able to create a valid path. So we go to C, then we go back to A, and then we go to B. So basically what we realized from this example is that sometimes in some of the cases we're going to have to backtrack. So we might go along an edge and realize that it doesn't work, and then we're going to have to reverse our decision and then travel along a different edge. So that's something we're going to have to keep in mind. Let's actually jump into the code in a second and stay tuned because it's actually going to be pretty tricky. But let's discuss the time complexity of this solution. And since I mentioned we are going to be doing some form of backtracking, the overall time complexity to run a DFS on the entire graph, in the worst case, it would be like a V plus E, right? Basically the size of the graph. But since we are backtracking, potentially for every single edge that exists in the graph, the overall time complexity is going to be the size of the graph squared. And since we know that the number of edges is actually going to be approximately the same or greater than the number of vertices, we can actually think of this as pretty much being E squared as the time complexity. And as the memory complexity, we can consider it to be big O of the number of edges. One, because we're going to be storing it in our adjacency list, and when we do the function recursively, this could be the size of the call stack in the worst case. So this is the time complexity, this is the memory complexity. Now let's code it up. Okay, so let's code it up. We are going to first create our adjacency list. We are going to map every single source node to an empty list initially. So let's go through every single source destination in our input, which is tickets, and just map the source to an empty list for now. And then let's actually build the adjacency list. So let's go through every source destination in our tickets, and then say for this source, we want to append to it this destination. And that's really all the pre-work that we have to do. Now we actually get into our DFS, where we are going to be passing in some source node and then running DFS on it, seeing if we can actually find a valid path, and then updating our result accordingly, right? Our result is basically going to be that path that we found that is valid and in lexical order. Now we know that we have a starting point in our results initially. We start at JFK, and we actually don't have to pass this variable into our DFS because our DFS is declared inside of the outer function. But now for the base case of this DFS, one is that we find our solution. How do we know if we find our solution again? Well, if the length of the result is exactly equal to the length of the tickets plus 1. And in that case, we're going to return true, saying that we did find a valid path. Now, one of the cases where we can't find a valid path is if this source that we're at is not actually in our adjacency list. What that means is that this source does not have any outgoing edges from it. In that case, we can go ahead and return false. That means we can't find a valid path. Okay, so now what we want to do is actually iterate through all of the neighbors of our current source node, right? So for this source node, we're going to go through all of the adjacent neighbors, and let's actually call it V. So for the input that we're given this source, we're going to go through all of its neighbors. We're going to call that neighbor the V, and we actually want to enumerate over this. And basically what enumerate is going to do for us is going to allow us to iterate over the index at the same time as the actual value, which is the vertex. But what you're about to see is actually we're going to be modifying the adjacency list as we iterate through it, right? Because if we visit this V vertex, this node, then we want to remove it. We want to remove the ith index from the adjacency list currently, but we can't really, update a list as we iterate through it. That's not really good to do, and in many cases it's not even allowed. So, rather than iterating over this, I'm going to actually create a temporary array of that. So I'm going to create a copy of it, and in Python you can do that just like this. Just pass that list into a list constructor, and that'll create a copy for us. And then let's iterate over that copy instead, because we want to be updating the actual adjacency list, because that's what's going to be used in future recursive calls. Okay, so we're visiting one of the neighbors. This is that neighbor. What we want to do is pop it from our adjacency list. So let's get the adjacency list of the source and then pop it. So we're popping the ith index, and once we pop it, we also want to append it to our result. What we're saying is this is our current path, so we can add that V, that vertex, to our result. And then what we want to do is run our DFS. I'm just going to leave that as a placeholder for now. And then if that DFS ends up returning true, then we can return true and then stop the function call, because we're just looking for one path. And we will know that that path is the smallest lexical order one because we sorted our tickets, which I just realized I forgot to do. So let's actually do that up above before we build our adjacency list. Let's not forget to actually sort our tickets. By default in Python, this will sort the tickets based on the pair, basically the logic that I summarized earlier in the video. But in some languages, you might have to customize that source comparator. Okay, but jumping back to the logic down here. So this is the decision that we're making, kind of in our backtracking. If we find that it returns true, that's great. But if it doesn't return true, then we have to backtrack this decision. So what we just did up above, what we did was we popped this. So instead of popping, let's insert it back into our adjacency list. So at this index, we want to add V back to it, and we added this to the end of our result. So now let's actually pop from the end of our result to remove that, right? Basically reversing this decision that we make and then making a new decision on the next iteration of the loop. Now, of course, it's possible that down this decision, down this recursive call, we don't find a solution. So in that case, we end up returning false from this function. But we know we are guaranteed at least one solution. So we know that when we actually call this DFS function, which I'm going to do right now, call the DFS, and we know that the parameter we want to pass in is JFK. That's always going to be our initial source node. So we pass in DFS, and then what we end up returning is going to be our result. And of course, this time it wasn't really the logic. I misnamed one of the variables. I don't know why I named it time. It should be temp. Okay, now let's rerun this. And I left our placeholder DFS as it is. We forgot to pass in the variable. We know that the variable is V. V is the node that we're going to be passing in. Okay, let's try this again. Okay, awesome. Now it actually works. You can see that it's pretty efficient on the left. This is a pretty challenging problem, but I think that this solution, while it's difficult, it is also doable for a hard problem. So I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon where you can further support the channel. And hopefully I'll see you pretty soon. Thanks for watching.
Okay, so realistically, I'm going to think of a depth first search. Adjacency, which is equal to source, empty, for source, and dest in tickets. Okay? So we sort the tickets. Tickets.sort. For source and destination in tickets, adjacency source, append the destination. Okay. Result is equal to what? JFK. Okay. Define DFS source. If the length of result is equal to the length of ticket plus 1, return true. If source not in adjacency, return false. Okay. Temp equals list adjacency source for I v in enumerate temp adjacency source pop I. Result dot append the V. If DFSV turn true, else source, insert IV, result.pop. Okay. Turn false. DFS JFK, return result. Okay, cool. You're given it.
Hey everyone, welcome back. And let's write
22-minute video. No music punishment.
some more neat code today. So today let's solve minimum cost to connect all points. And surprise, this actually is not a problem from the blind 75 list that we've been working on recently. And the reason I'm solving this problem is because honestly, it actually should be a part of that list. Like this is one of those problems I think that's missing from the blind 75 list. Reason being is this is a problem related to minimum spanning trees, a concept that a lot of people skip over, I think, when they grind Leetcode. So this is what we're gonna be doing today. And you might have heard of an algorithm for minimum spanning trees. There's actually a couple, Prim's algorithm, and there's also Kruskal's. We're gonna be doing Prim's algorithm because I think it's easier to implement and it's actually more efficient most of the time. And you might remember this algorithm from college. Most computer science curriculums do teach it, but if you're anything like me, you probably forgot it the instant that you finished the class that you learned it in. But that's okay. And this algorithm, Prim's algorithm, is actually not as complicated as you might expect. So we're just given a list of points that represent some coordinates on a 2D plane. So for each point, we're given two values, the x coordinate and the y coordinate. So the cost of connecting any two particular points, like let's say these 2 points circled down there, the cost of connecting them is just going to be the absolute value of the x difference plus the absolute value of the y difference. So it's actually not, the cost of connecting them is not going to be like the diagonal. It's going to be the x distance and the y distance. In other words, the Manhattan distance, if you've heard of that term. That's pretty easy to calculate, good for us. And for the entire set of points, in this case, we're given 5 points. We want to know what's the minimum possible cost to connect all points. And they also say that any pair of points is going to be connected by exactly one simple path. I think that information is actually redundant. Just saying that we want the minimum cost to connect all points pretty much tells you this is going to be a minimum spanning tree problem. So the only question is, where the heck are the edges for this graph? We're only given points, right? So, but they do tell us pretty much what an edge is going to be, right? The cost of each connection is just going to be the distance. So we have to create our edges ourselves. So basically, all possible edges could be, every single point to connect it to every other point, right? That's going to be a set of edges, and we can continue that. So for example, this point to connect all the other points as well. So we're going to have to kind of manually create the points. So for each pair of points in the entire graph, we're just going to take the Manhattan distance between them and just call that an edge, and then have our list of edges, or basically we're going to create an adjacency list. So that is kind of like the pre-work we have to do. That's step 1 in this problem, creating the edges. But as soon as you create the edges, this is literally just a problem that you can go ahead and take Prim's algorithm and just apply the textbook definition of Prim's algorithm to this problem, and you will get the optimal solution. And the time complexity of that is going to be n squared log n, because n squared is going to be the number of edges we're going to have, right? Because to connect each pair of points, we could potentially have n squared edges, where n is the number of points that we're given, and log n is going to come from Prim's algorithm because we're going to be using a min heap in this problem. So it's pretty similar in a way to Dijkstra's algorithm, to Dijkstra's minimum path algorithm. If you're familiar with that, Prim's algorithm is pretty similar to that. So let's jump into it. So Prim's algorithm is an algorithm to find minimum spanning trees. So there's a few concepts you have to be familiar with to understand Prim's algorithm. Obviously, you need Prim's algorithm to solve this problem efficiently. So I'm just going to give some of the background in case you don't know it. So basically, let's say you have a graph, and in this case, we have a graph with 5 nodes or vertices, right? And to connect all of these nodes together without forming a cycle, so we want every node to be connected together, but we don't want to form a cycle. How many edges is it going to take us to accomplish that? It's going to take exactly n minus 1 edges. So if we have 5 nodes, it's going to take exactly 4 edges to connect all of them together without creating a cycle. Because take a look right now, I have 4 edges, right? If I add another edge that's not a duplicate, if I add an edge here, we create a cycle. If I add an edge here, we create a cycle. If I add an edge here, we create a cycle, right? That's just kind of something and I think it intuitively does make sense because, if you start out with 5 nodes, you add 1 edge, now we have 4 different, connected components. We have one here, and then a couple here. Every time you add an edge or
decreasing the total number of connected components by 1. So if we start out with 5 nodes, we add 4 edges, we decrease the number of connected components by 4, then we're going to be left with 1 connected component. So if we add another edge on top of that, we're going to get a cycle. So we want to connect all of these without creating a cycle because that's what a minimum spanning tree is. So our goal is to connect all of these with exactly 4 edges, but Prim's algorithm, or the definition of a minimum spanning tree, is also one more condition. We want to minimize the total cost of the edges. Now, I didn't actually draw all of the edges, all the possible edges out right now. It would look something like this, right? Basically, for every single node, it could possibly be connected to every other single node. And the reason I'm not drawing it is, as you can see, it's going to get really complicated really quickly. So this is pretty much what it would look like if I drew every possible edge that could exist in this graph. And I think that's going to make it a little bit too messy, but let's just assume that those edges do exist, that for any point, we could possibly connect it to another point. So the way Prim's algorithm works is we can choose to start at any single node in the entire graph, and then, very simple, we're just going to perform a BFS, a breadth first search, on that node, where we are going to continuously, for every node that we're adding, we're going to have 2 data structures. We're going to have a visit data structure to make sure that we don't add the same node twice, because if we add the same node twice, that's how you know we're going to get a cycle. We want to avoid cycles. The second data structure we're going to use is a minimum heap, which is going to keep track of our frontier of our breadth first search. Now, what is a frontier? Well, you might know that, let's say we had a single node. So we visited this. This is in our graph, right? This is part of our minimum spanning tree. What's the frontier then? Basically, every possible node that could be added from this position, right? So initially, if we just had one node, these 4 nodes would be in our frontier, but we're not just going to have each node in the frontier. So we're going to have, let's say node 1, and we're also going to add the weight of connecting node 1. So let's say the weight of the edge was something like 5, then we'd add 1, 5 in our min heap. But we're not going to add it in this order. We're going to add it in the opposite order, 5, 1, because when we're popping from the min heap, we're going to be wanting to pop whatever node we can connect next with the minimum possible cost. So let's say we had 5, 3, 2, and up here we have a 6 or something. Out of all these 4 nodes, which of them can we connect with the minimum possible cost? That's what we're going to use our min heap for. Looking at it, you can tell, okay, this one because it has a cost of 2, so then we're going to connect that. So then that's going to be a part of our frontier. So next, we're going to say, okay, we have 2 nodes, a part of our frontier. Next, what we're going to do is add more nodes to our frontier. Even though we already had all 3 of these nodes, we're going to add them again to our frontier, because now possibly if we're starting from node 4 and we're trying to connect to 3, 1, or 2, it's possible that the connection from 4 to 3 or 4 to 2 or 4 to 1 could be smaller than the connection from 1 to those respective nodes. So we always want to connect a node with the minimum possible cost that it takes us. If it costs less to connect it to 4 than to connect it to 1, we're going to take the one with the smaller cost. And of course, as we visit nodes, we visit 0, we visit 4, we're going to add them to our hash set so that we don't, starting from 4, we're not going to go back to 1 and add 1 again, because that would create a loop. And how do you know that we can stop the execution of Prim's algorithm? Well, once the length of our visit set, the number of nodes that we've added, is equal to 5, which is the number of nodes that we started out with. So with all that being said, you just have to understand how these data structures are contributing to the solution, and then we can go ahead and walk through it. So let's start at 0. You can start at any node. You can start at 3, 2, 4, but in this case, we're going to start at 0 just because it makes sense. So when we start at 0, what we're doing is we're adding it to visit, and we're adding it to the frontier. So what's the cost of connecting 0? Well, if we're just connecting a single node to the graph, we're not actually including any edges, so the cost is going to be 0, and the node value is going to be 0. And so the way this algorithm works is at each step, we're just going to pop from the min heap. So let's pop the first value, this, right? So the total cost so far is 0, right? We don't actually have to add any cost. And that's actually one other variable we're going to be maintaining. Let me just write it down here. So far the cost is 0. We're going to continuously be adding to it though. But next, for 0, we're now going to add every one of its neighbors to the frontier. And the way we're going to add it, I haven't drawn it out, but there is going to be like an adjacency list. So we will have a list of neighbors for 0. Of course, it could be connected to every single.
Hello?
Hey girl, what you up to?